Hi everybody. Let me unblock my tablet because I don't remember what should I say. Maybe I should start from introducing myself. My name is Evgeny Ivanov. I'm software developer at VDB, which is part of Yandex Cloud. And I'm happy to greet you today here. Welcome back to back. Enjoy the conference. Previously, this conference was called C++ Zero Cost. But I assume that most of you know that it's a lie, because there is no zero cost. Everything comes with a price, especially bugs. So we have also online audience. Today this conference takes place in Moscow, in Belgrade, and in Yerevan. So we are really happy to see everybody here today. Please enjoy the conference, and let me give you a chance to say something to my co-speaker Gosha.
Всем привет, меня зовут Георгий Осипов, я работаю в Яндекс.Лавке и очень рад приветствовать вас на нашей конференции. Очень хочется сказать C++ Zero Cost Conf по старой традиции, но сегодня я вынужден сказать, что наша конференция называется Back to Back, и C++ это только один из треков на ней, так что я думаю, что конференция стала еще интересней, и наша белградская программа сегодня посвящена в основном как раз C++ по традиции. Поэтому я уверен, что здесь собрались истинные ценители и истинные любители. А вообще конференция проходит сегодня в 3 городах. Это Москва, Ереван и здесь, Белграде. И, конечно же, каждый из этих треков можно смотреть онлайн.
So we will be your hosts through the day. Please enjoy the conference. And I know that it's really hot outside, but we have a really hot topics today. So please feel free to go outside to cool down.
Сегодня в Белграде довольно жаркая погода, но здесь будет еще жарче. Конференция будет, как и раньше, на 2 языках, русском и английском. Если вы вдруг не понимаете один из этих языков, то вы можете взять специальный headset, в который будет перевод. Если вы еще этого не сделали, то еще не поздно. Так что можете это сделать. У нас сегодня очень разнообразная программа. У нас будет 6 докладов про новые возможности C++, 26, производительность, сетевую разработку и низкоуровневые механизмы оптимизации. Достаточно интересные темы.
Also, at 3:50 there will be a workshop about agentic coding. For you, it's a great chance to face creatures who pretend to take your work. Also, at 5:40 you can join a guided tour to the Robo-Ruka space. Robo-Ruka is a robo-hand, I guess. And our Yandex team will introduce their robots and projects. I hope they obey 3 laws of robotics.
У нас будут 2 перерыва. На первом из перерывов вы можете посмотреть на гонки роботов и также насладиться ланчем. А после второго перерыва вы можете пойти на воркшоп по агентной разработке, который проведет Сергей Федоров. Он запретил употреблять слово вайб-кодинг, поэтому мы называем это агентной разработкой. После конференции мы также с вами не прощаемся. Вы сможете пройти на экскурсию по роборуке и затем на автопати.
Please don't forget to take breaks. Not because talks are boring, they are not boring, but take breaks because it's a conference. It's not about speaking on scene. It's about you, participants, speaking to each other, sharing ideas, sharing your experience. Please take breaks, share ideas, do some networking, meet your new friends. So enjoy.
Как сказал Женя, конференция — это не только про то, чтобы слушать доклады, но и про то, чтобы общаться между собой. Я надеюсь, что вы найдете единомышленников и познакомитесь с интересными людьми. И самое важное — это QR-код, по которому можно присоединиться в чат.
And of course, there will be after party right in the opposed to the Yandex office. There is a great bar called Rodina or Motherland, whichever you prefer. Today it's a common motherland for both people from Russia and Serbia. We have now single motherland. So please join after party, enjoy motherland, and have a good time.
Автопати пройдет в баре «Родина», это совсем недалеко, но мы еще позовем вас туда. Еще будет время. Что ж, я думаю, что самое время начинать Back to Back 2026.
Yeah, and a little reminder about party. Little party never kills nobody, so enjoy.
Мы еще должны представить спикера. Евгений, самый первый доклад у нас будет про построение самого маленького помодоро приложения, который представит Милош Анджелкович.
So I forgot that I should tell about speakers here, not about my own feelings. Our first speaker is Milos Angelkovic, and he has a really great talk about tiniest Pomodoro app ever. And I think it's a very important talk because it's an art to write tiny applications. If you check your memory consumption on your computers, you will see applications are greedy. And now we have Pomodoro app which consumes a little of memory, and it's an art. Please, Milos, welcome to the scene. Dobro došli.
Can you please check the clicker? Your place is there. Yeah. Can you please check your, can use clicker? Okay, it's fine. So, begin.
Yeah, thank you. So I wasn't nervous until they said it's a great talk, and now I feel like I need to deliver. About me, I'm a software engineer, like I guess most of you, currently working in Rust. Don't be mad. Other than that, I actually started as a teaching assistant, and like I want to go back to that. So now the plan is to go and work in elementary school, and I did some studies for that. Other than that, I volunteered at a children's shelter. These two are not relevant to the talk, but if you want to talk about it, I'm here. And other than that, I organize meetups in Prague from Baric, technically. And also I'm a member of C++ Serbia, so if you want to join any of that, we can talk later. But also there are other people from those meetups. So what even is Pomodoro? For those of you that don't know, it's basically a studying or working technique. You do 25 minutes of focused work, and then you take 5 minutes break. Basically, you get up, stretch your legs, stretch your whatever, or if you have a standing desk, sit down, relax. And then every 2 hours, basically, you take a 15-minute break, which means you can take a nap every 2 hours and say it's, for productivity. And you repeat that until you can't anymore. And I just wanted to install a Pomodoro app. It should be small and simple, right? I have Linux Mint with Cinnamon, and I go to the software manager, and there is a Pomodoro app, and then I look at it, and it's 200 megabytes to download and 2.7 gigabytes to install. Ridiculous. In this economy, with these memory prices, too much. Now, this is because I use Cinnamon and it needs to install GNOME, but when I went to the Git, it says it's less than 4 megabits. Now, I don't know why they decided to use bits instead of bytes. Maybe they don't know the difference, but I don't want to talk about badly about someone who's not here. So, let's say this is 500 kilobytes, which to me is, still too much. Again, based on the Git README and stuff, like it looks like the author has good intentions, but maybe good intentions are not enough. Maybe you need some actual skills. So I talk with my team lead, and he basically just takes out his phone, goes to ChatGPT, and says, like, build me a Pomodoro app, and it does HTML, CSS, JavaScript, and it's 20 kilobytes. I mean, 20 kilobytes without the actual browser that you need to actually run the thing. But I decided, okay, this is gonna be my benchmark. I'm gonna try and build a Pomodoro app in C++ that's gonna be less than 20 kilobytes. This is how it looks. I mean, it looks nice, much nicer than anything I'd be able to build. And it works like the most important thing. So the quest to build the tiny Pomodoro. First iteration is using FLTK, fast, light, like it's in the name that it's light and it's small, but it does have a lot of dependencies, obviously. It has windows, it has buttons, it has event loop, it has all the nice stuff that lets you write actually nice and simple code, and it abstracts over a bunch of stuff. Plus it has add timeout, which is kind of the core of the timer. The code itself, now I understand there are raw pointers here, but don't be afraid, it's okay. They don't own anything. The FLTK takes care of memory. They are here just to point to stuff. The point is the types. You see you have box, you have button, input, and stuff like that, and then, okay, these are some helpers here. You create a box, you create a button, and again, the FLTK itself, like when you create a window, it starts some context. Everything you create until you end the window goes into the context, and then when the window is destroyed, it's going to free everything. And then you have a callback, which is just like the time ran out, how much time is left, is there any left? If it is, if there is no time left, switch to the next session, sleep again and over again. And this is how it looks. I mean, by my standards, pretty nice. And the build is 1.1 megabyte. I mean, the release, the others are there, but the release is what's actually important, which is way larger than what GPT created. So the code itself is, I mean, perfect. There is no room for improvement, but we can work with flags, and we can work with a bunch of flags, 15 of them in total. Now, just like quick overview, this is how the compilation generally goes. Like you have a front end that turns your CPP file into abstract syntax tree. Then you have this intermediate representation generation, which turns it into LLVM's representation. Then you optimize. Then you do the code gen, which turns it into like the actual machine code. And then that's when you get the .o file, and then the linker links stuff, and then the loader loads it. And this is just a quick overview of all the flags and where they actually work. But don't bother reading all of them. We'll go through it. The basics is the OZ or OS. I think the results vary, but they should be pretty similar. Like I went for OZ, and this is like mini size. This is just do whatever you can by default to make a small binary. No inlining, no vectorization, no any of that cool stuff. The performance is worse, but it's like 99% time sleeping, so we don't care that much about the performance. This is your basics. This is like, you know, you work out, you sleep, and you eat well, and that's where you get like consistently 50% of your gains. I understand that gym references might not be the best for this crowd, but I've decided to roll with it. So, and also it took some effort to find the proper comparison, so I need to make the effort pay out. The other thing is the no exceptions and no runtime type information. Basically, if you don't use the exceptions, don't like just disable them. If you don't use runtime time information, disable it. There is a bunch of stuff that the compiler needs to generate for you to be able to use this stuff. If you don't use it, disable it, and the code is just, the generated code is going to be smaller. This is cutting out junk food. Now, I do feel bad about comparing exceptions to junk food because they are actually useful, but if you don't eat the junk food, then you don't really lose anything. And of course, you need to be careful, because if you are using a library that throws exceptions that you need to handle and you disable exceptions, you're going to have a lot of problems. Or maybe not a lot, but you're going to have some problems. And now we have this LTO, link time optimization. It basically reorders your compilation. So now, instead of like taking a CPP file and then do the pre-processing and all that stuff until you get an actual .o file, you take the intermediate representation directly and then send that to the linker. And then linker, now that it has all of your translation units, can do optimizations across the whole program instead of just individual translation units. So basically, the linker sends it back to LLVM, and then LLVM does the optimizations and all the cool stuff. And then in the end, again, you get the code gen and linking and all that stuff. And I mean, in essence, if you have a function in one translation unit, then you need to have it like compiled, because even if you don't use it within the translation unit, maybe someone else somewhere else will use it, and you don't know. When you do this, you can actually look all of the code and see, okay, well, this isn't really used anywhere, so I can remove it freely. I'm sorry, it's really confusing because the speaker is right here, and I hear myself, and I talk, and my voice is very annoying. Okay, this, in gym culture, this would be planning for the whole week. Instead of like taking each session individually, you actually take into account the whole week or a whole month and plan accordingly. Now, there is a bunch of these flags. Well, there's a bunch, there's 4 of them, but okay. Function sections and data sections. Basically, in your actual ELF file, the thing that you execute, or the .o file, you have sections like .text where the code goes. And it's like one huge blob. If you do function sections, then you're going to have a separate section for each function. It's going to be .text, .function1. Well, it's going to be mangled name, so it's going to be uglier than that. But it's going to be like .function1, and then you have text, .function2, and so on. Similar for the data sections, but in the BSS or raw data or data. And once you have those sections, then you use the GCC sections, which actually happens during the link time, and it can look at the sections that are, again, not used anywhere, and it can remove them. So the difference between like link time optimization and this is the fact that this takes into account like the broader picture. The link time optimization sticks to your code, the stuff that you wrote, and this is like including the stuff from other libraries that you link to. IFC is like instruction something folding. Basically, again, it's going to look at the sections, and it's going to see if you have functions that are identical. Like if you instantiate a template with 2 types, and I mean the types are different, but the actual machine code is the same, then it's going to fold them into one function. And you have marginal constants, which is basically the same thing. You have a constant, you have like 5 constants, and all of them have the same value but have different name. They are going to be all merged into one. This is not standard compliant because the standard says that every distinct variable is going to have its own address. So, I mean, it saves some memory, but you're no longer standard compliant. Now, in terms of gym stuff, this would be your bulking and then cutting phase. So bulking is the first 2, and then the second part is cutting. And I see the gym references are not landing at all. But okay, I'm going with it anyway. And then we have unwind metadata. Well, basically, if something happens, I mean, if you throw an exception, then the compiler needs to figure out like who is going to handle the exception and where and how and why, and also the debugger, if you break somewhere, it needs to know like the whole call stack, the profilers and all the stuff. And all the data is stored in these unwind tables. There are two of them. There is asynchronous and synchronous, I guess. The synchronous is supposed to contain data that's valid for the case where you throw an exception. Meaning like only for the places where the exception can actually be thrown, which is much less than the asynchronous. Asynchronous means for each instruction, you need to be able to figure out where it is in the code and like in the code stack and how it goes. This means basically if you call a function and something goes wrong during the setup of the call stack itself, so like you're exiting one function but you haven't actually entered the other one, if that happens, like the synchronous unwind table should be able to tell you how to figure out where this comes from. This actually works together with the exceptions because again, exceptions are a big user of these unwind tables. Okay, and also like by default, at least on my machine, but I think it's the standard on x86-64, the asynchronous unwind tables are used and they automatically apply the unwind table. So if you disable them, nothing actually happens because you're really using this thing. If you disable that, you get some savings, and then if you actually also disable the exceptions, then you get even more saved. This would be basically logging your workouts, like what you did, how many sets, reps, and all that stuff. Helps to figure out where you are, and if you want to repeat something or something went wrong. And then the symbol surface, which is basically about the stuff that you export and the stuff that you import or include. But let's say import. There are these three separate things. So you have din.sim, which is about the stuff that the symbols that your binary exports that can be linked against. And like by default, everything is exported and everything has an entry in this table. And if you say visibility hidden, nothing is exported by default, and then you have to manually say like attribute public, I think, or something like that to actually export it. And also like if something is hidden and it's not used, then the optimizer can also remove it. And you need to be careful. Like basically everything here is just trying to remove as much code as possible. So if you want something to stay, then you need to be very explicit about it. WL, like by now we understand that WL means this is something that goes to linker. As needed, this is so about the stuff that you link against when you're like compiling your thing, and then you say L X11, L this, L that. Like those are all of the libraries that you want to link against. However, it can happen that you don't really use all of that stuff, especially if you're linking against a library that's linking against a bunch of stuff, and all of that comes to you, and all of that has an entry in this table, and you say as needed, which means like only if I use at least one symbol from this library, keep it, otherwise don't. And without this flag, I think there are like 37 libraries that my app links against, but with this it's 12. And then SIMD is again another table, and it has all of your symbols, and it's used by debugger when you like, well, I mean not just debugger, but basically by debugger to figure out when you're stuck somewhere, like what's actually what's the name of the variable or whatever, and so that you can find it in the code. And if you say like -s, which is strip, it just removes the whole table, makes the debugging more difficult. And if we do all this, well, we actually save quite a lot of space. It's like 300 kilobytes, but it's still like much larger than the GPT's thing. The reason for this is the code. I mean, the code that I wrote, the Claude wrote, is actually 350 lines, and FLDK is like 3.3 megabytes, and it doesn't get any, like it's built with O3 and I don't know, some basic flags. It gets none of the optimization stuff. So if we, and again, like link time optimization stuff happens only on my code, on stuff that I wrote in my program. And some of this link stuff can help, but not that much. However, if you decide to build the FLTK as part of our application, then it goes down to 327 and whatever bytes, which is like 61%. Now all of those flags that we used go, oh, sorry, I forgot the gym reference here. Very important. Now this one actually was the hardest, and this I think would be the selfie. So you take a bunch of selfies, but you choose what you're going to post online. Yeah, this one was definitely, that's why I forgot. It was the most like tense thing, really not really difficult to relate. Anyway, we saved like a bunch of stuff, and this, this I came up with this morning actually. This would be basically, instead of just taking some online program for your workouts, you put in some effort and adjust to yourself. But when you do this, you can't really blame the others. You have to take the responsibility. So make a choice. Now, on that note, if you are building someone else's library and you are putting your flags in there, you don't know if it's going to build properly. You don't know if they're using exceptions or runtime time information, or I don't know, maybe you fold some constants, but as it turns out, they actually depend on them being on different places. So you need to be very careful if you do this stuff, and in general, you don't really want to do this. This is just to build the smallest binary, which still turns out to be way too huge. So that was the tiny Pomodoro, but it's 2026. We have a pro version, which comes with a subscription. It's a very small fee, don't worry. Now, unlike modern companies, we go the other way. We remove stuff. So now we're not using FLTK, we are using X11 directly. X11 is Linux protocol, like you send it messages, you send it like draw this, and then it gives it back to you and stuff. The point is, it's more difficult to work with. Now we don't have the buttons and we don't have the widgets and all that stuff. You're just like drawing stuff by hand, like a caveman. But you have 40 times less dependencies. And also, like, you need to actually implement the timer yourself, which like requires a thread and all that stuff. The code, don't go too deep into it. The point is, like, you can just visually see it's uglier, right? A lot of setup you need to do yourself. And then when it comes to drawing, like draw center, like you need to figure out like how much space you have from the left and the right, and like to center it properly. And then like you draw the point is like you're drawing, like you're not creating a button, you are drawing. However, okay, this is how it looks. It's not bad. It works. That's the important part. However, the size is like 15.9 kilobytes, which is less than, and this is like standalone binary, so you don't need Mozilla or whatever you use. Like it just works, right? Again, 2026, there is a higher subscription for Pro Plus version, and we are keeping the same theme. We are removing stuff, so now we're not using GUI at all. Like we are working with the console directly, and it's not even like STD print or cout or whatever. It's Termios, and that's just to be fancy. You don't have to do it, and there is no even sound. You just use like \A to ping something. The code. The point of this is like you actually take control of the terminal, and this is done because you actually, because you don't want to press enter for the command to happen. You want to react as soon as you push a button. And so you have a setup terminal, but also you need to restore it later so it keeps working once the application closes. The rendering, unintelligible when you see it this way, but there is going to be a screenshot. And then you have the actual loop where you basically handle the cases, and then again, the timer is actually shared between this and the previous version. Yeah, like then sleep and the standard stuff. This is how it looks. Now you can ignore the fact that there are those because it looks amazing. Let's be honest. Ignore those lines. To be honest, my first version was you just pass the values as command line arguments, and that's it. This actually lets you change stuff while it's working. It's amazing. And when you look at it, it's 9.7 kilobytes. So this is half the thing that JavaScript, HTML, CSS, JavaScript was. You know what's coming next, right? So there is ultra version, right? And we only add superlatives, we never remove it. It's pro plus ultra. And we go raw. We do it in assembly. We removed basically everything. It's total insanity, and it doesn't even use libc. It uses nothing. It works. The code, now I don't even wanna bother because I don't understand assembly, and it's obviously generated. Claude knows what it was doing, but I don't know. I'm gonna keep it here for the later recording if someone wants to pause and actually read it. But it's also on GitHub. The point is that actually what Claude did was he basically copied entirely the previous version in terms of looks and behavior and all this stuff. And okay, I messed up the slides. So this is how it looks. It's basically, it's even better. No, it's not. Nah. Okay, the lines are misplaced, but it's basically the same as previous version. Now, as far as the flags themselves go, OX is it's a flag for an SM, the assembler, and it's on the first pass is going to encode very, let's say, generously, with large encodings. And if you pass this flag, then it's going to do a multiple pass, and then it's going to figure out that some stuff can actually be encoded with smaller, let's say, instructions. Other than that, no stud lib, so no stud nothing. Static, meaning it's going to be a static binary. There's not going to be the whole dynamic. There's not going to be a table for the dynamically loaded stuff. And S is again, as in Tiny, the strip the debug symbols. Okay, this is how it looks, and it's 8.8 kilobytes, which is less than 9.3, I think, which was the previous version. So that's so much for the zero cost abstractions. There is always some room for improvement. But actually, the disk size actually stays the same because it needs to be aligned to a whole page, and that's 12 kilobytes. And this is the comparison between all of them. So as you see, we go from now the numbers themselves. Okay, to be clear, don't get too attached to the numbers themselves, because if you build this on a different system, you're gonna get different numbers. But the trend is the same. So if you just build, you get something huge, and then if you include the thing into your build, you get something smaller, and then the more you remove stuff, it just gets smaller and smaller. And the big realization here is that the best features are the features you don't implement. They don't bug, they don't need to maintain them, they're just perfect. So yeah, try to remove. It's a tough sell for management who just wants to push stuff in there, but yeah, the less nonsense you have, the better your application is going to work. But there is a 2 version. Yeah, there is a 2 version, and the 2 version is the ultimate version. It's pure assembly, has no UI, it's just, you do not configure anything. There is no interface, there's nothing. It just works, it sleeps, it rings, it sleeps, that's all there is to it. It's a couple of lines of, it's 100-something lines of assembly. However, the size is only marginally smaller than the Pro Plus Ultra version, and even though it's like 25 times less code. And the reason for that is, well, if you look at the sections themselves, they are actually very small. It's only if you look at the actual code, it's 420 bytes, but the actual on disk size is 8,000 something. And that's because basically different parts of your program need to be on different memory pages. So, you know, the loader like loads them in segments and like it does mmap. And basically like your code needs to have read and execute permissions, and your data needs to have read write, and static data, not static data, like const data needs to have read only, and you need 3 separate pages because you can set the permissions on a page level. And so you need like at least 3 pages, which is, well, technically 2 pages, and the third one is kind of truncated. That's why it's 8 point something kilobytes instead of full 12. Now you can go even lower than this. There is this blog. It goes down to 45 bytes, not for a Pomodoro timer. It's just like how tiny can you be. You overlap the sections and you do a bunch of stuff. I mean, 45 bytes does basically nothing. It's almost only the elf header, but you can go that low if you put some effort into it. And yes, so the overview itself, well, yeah, just like put in some effort and things are going to be slow. Well, yeah, they're going to be slow, but they are going to be small. And yeah, I mean, again, I had a bunch of stuff happening, so I let Claude do all of the coding. I mean, he did most of the presentation even. But, you know, like you still need to, like your biggest input in this age where, you know, you have a tool that can actually write the code is realizing that 4 megabytes for a Pomodoro timer is too much. And then, like, he's going to do whatever you ask. You just need to be the one that realizes that things are actually wrong. Oh, they added the QR code. Nice. Yeah, this is the link to the GitHub, and it also, like, includes the notes and the explanations of the flags and, like, much more details about everything if anyone wants to read. And that's all I had to say. Thank you.
Milos, thank you very much for your speech. It was very interesting. We learned a lot of compiler flags we never heard about and elf structure, and that was very interesting. Next year, we are looking for 20 kilobytes version of Grand Theft Auto 6. And it's time to ask questions. I think Evgeny has.
I would like to use my privilege having my microphone in my hand already and ask first question. First of all, thank you so much for a great talk. I really enjoyed it, but there is one thing I really didn't get.
Oh, sorry. I forgot the gym reference. Yeah, I have it for this one. This is a superset. It's like the OX is a superset. It does very little and it's like difficult. So yeah, I don't have one for the 2 version. Okay, sorry.
So my question is actually, should we wait for Pomodoro 3 application this or maybe next year, right before GTA 6?
I think GTA 6 is for November, but if you're talking about PC version, maybe. Yeah, I don't know. I like for all of the stuff that I did and looked into, it's usually a rabbit hole, and you can go very deep. And at one point, you say, "Okay, I mean, it's enough." So I didn't go into this whole going lower than the memory pages, but well, maybe if I have time, I decide to do it.
But you almost achieved 1 memory page for 4K, and
no, it's 2. It's at least 2.
Yeah, sure. Right.
Yeah.
So there is some space.
I mean, there is a lot of space. It's 95% empty space, so there is a lot of space. It's just, do I want to hack it at the heart?
Thank you. So I believe we have a lot of questions. Please ask your question, but probably please wait for microphone. So could you please? Yeah.
Yes.
So thank you for your presentation. Yeah, it was interesting stuff. But I would like to return to the previous page where the sizes were. So we are talking about the ChatGPT implementation. It's 20 kilobytes, but I think the main thing which were missed, it's about runtime. Because if with runtime, yeah, it will be the same sizes as the software manager. So you won on the first iteration here.
Yeah, true. Yeah, and also like some of the stuff, especially when it comes to those tables for dynamic linking and debug symbols, like some of the stuff is only on disk and some of the stuff is actually loaded into memory. So there is a difference between disk and RAM usage, even with these numbers.
Yeah, because I thought during your presentation, I was thinking, and why should I use C++ if you're talking about the kilobytes, if I just can use Python, and the realization will be much more or less size.
Well, yeah, because for Python you need the whole interpreter to run and all this stuff.
Yeah, the same thing with ChatGPT implementation. Yeah. Thank
like
you.
the ChatGPT has this advantage that, like by default, you have a browser on basically everything that's connected to internet. But yeah, if you want something that just runs, then build it.
Next question. Okay, we have a question.
Hello, thank you for your talk. I have a question about your switches for sections in the final L file. Do they do the same as strip application? If you just called strip I need it on the final binary, would result be the same or different?
I don't know about the strip unneeded flag, so I don't know. I only know about the strip that removes debug symbols. I don't know about strip.
It's usually the final stage of CI pipeline before you release. You just strip your binaries and it removes debugging symbols, unneeded sections, and it can also strip a lot of data from builds which are built in release mode. So you build release mode and it still has loss inside.
Yeah, because like again, a bunch of stuff you can't optimize because you link against it, and then only once you have your binary can you like.
I feel like it does the same as these flags.
It's probably.
That was an idea for Pomodoro 3 Plus Ultra exclusive.
Yes.
Thank you for your talk. My question may be regarding the next version. If you move this Pomodoro up to a separate microcontroller, can you go even lower in the size?
Maybe. I don't know how the controllers handle the pages. So if you don't have, if you're not limited by the pages or page sizes, then you can go lower probably. I mean, I think just compiling the Plus Ultra version, Pro Plus Ultra version for some controller that doesn't use mmap and for kilobyte memory pages would help.
Еще вопросы можно по-русски задавать. В последнем ряду есть вопросы, есть руки. Давайте.
Hello. Perhaps one way which we could use to decrease the executable by even more is to merge all sections, both code data, into one. And the list of sections will be smaller and it will give us several bytes less executable.
Yeah, I think it's not several bytes, it's going to be a lot of bytes because, again, separate sections need separate pages, and if you merge them into one section that uses one page, then basically comes to that.
It is not a good thing to do, but still it can be done.
Yeah, a lot of stuff can be done.
That's it.
More questions? We also accept questions in Serbian language. So if we don't have questions right now, please ask your questions during the break. And let me remind you, there is a fancy QR code, and I kindly ask you to take your phones, scan the code, and rate the talk. I'm serious, we will not continue until you rate the talk. I will count everybody.
Я повторю, чтобы все точно поняли, что тот QR-код, который вы видите, он хоть и очень красивый, но он не для красоты. Нужно обязательно его сосканировать и оценить доклад Милоша.
Milos, thank you so much for your talk. It was really enjoyable. Thank you. So it's time for our next talk. Next speaker is very special for me because I meet him every time on every conference I visit, but even more before. So you decided to come earlier.
Can you stop talking?
Oh, sure. No worries. You can stand in the middle. Okay. So take photos. We are with our starters. First time I met Alex, it was our GitHub issue page. He suggested a very strong changes in our release cycle to make our product better. And also, according to the Serbian law, please be advised, this person is addicted. And his addiction is PGO, Profile Guided Optimization. And today he will talk about taming the pitfalls in the name of performance. So that will be really interesting, and please apply this technology to your open source projects before Alex goes to a GitHub issue page. He will force you to do it anyway.
Наш следующий докладчик прямо перед вами — это Александр Зайцев, и он расскажет нам про Profile Guided Optimization. Я даже не буду пытаться переводить это на русский язык, поскольку я думаю, что если вы не знаете, как это переводится, то вы узнаете это из доклада. Вот, Александр, самая важная вещь — это найти кликер. Давайте поищем кликер и проверим, насколько он работает.
Now you have not just talk, but also a quest.
Yep, it works.
Супер.
It's time for us to leave and leave you alone with the audience.
Yeah, I think so. So, hi everyone. My name is Alex, and today we're going to talk about some compiler optimization stuff, a little bit about under the hood stuff and data-driven optimization. So, a few words about me. Yeah, I am also transitioned from C++ to Rust. C++ was my favorite toy for many years, but I just decided. Okay. Okay. So now I use Rust. Also, like I've spent several years applying PGO for multiple open source projects and some not so open source. And one detail that I prefer to use LLVM stuff, so please expect more LLVM stuff from me. I still know about PGO in GCC and a little bit about MSVC, but who cares about it? But anyway, so maybe you've seen this post about like my transition process into Rust. So regarding PGO stuff, actually, there are, for the last couple of years, there are several talks at multiple C++ conferences, not only about C++ conferences, about PGO stuff. But most of them are focusing on internal details about how PGO works in compiler, which parts of compiler can be improved by it, etc., etc. I wanted to create something a bit different, what you will meet in practice when you will try to apply PGO for your application from multiple perspectives. So our content for today, so what PGO is, just a quick recap because it's kind of boring stuff. Few words about different kinds of PGO, the good and not so good sides, and about the C++ situation and the PGO, like what do we have right now in our ecosystem and what can be improved. A lot of things can be improved. So why should we care about PGO? Because PGO works, and PGO works pretty well. Just applying one optimization, like a data-driven stuff, we can improve performance of our application, not only application, it applies to libraries too, in quite significant way. You see a lot of up to, because it depends on the benchmark, depends on the target workload, etc., and sometimes you can get more performance, sometimes less, but anyway, that's kind of on average. And of course, it's working not only for C++, and working for different languages, like for example Rust-C, because it's written in Rust plus C++. Why do we need PGO? Because, okay, we have two major compilation models, ahead of time and just in time, and unfortunately in C++ our major model is ahead of time, and in our world we don't have a good ability to gather the runtime statistics about how our application is executed. In just-in-time world, there is some interpretation machine that can try to collect this information. For example, that's how in Java world it works, like in JavaScript world, or in Python. In C++, we don't have such a privilege, and we want to have it because there are a lot of optimizations in our compilers, and C++ compilers are good, at least from this point of view. And we can improve a lot of optimizations by just providing a data about how our application is executed. For example, one of the main optimization, inlining, can be significantly improved, and even LTO stuff can be improved by PGO. It's just one comment in the internet, and FinLTO can be improved by it. So our solution, like we see, you see a lot of passes with just like screenshot from LLVM page, and you see some, for example, there's a screenshot from LLVM sources, and you will see some predefined constants, and of course they're probably okay for some generic stuff for general application, but we can try to tune them to our specific application, our specific workload. So, what kind of PGO do we have in C++? Actually, it's kind of complicated question to answer because there are a lot of them. So let's start from the common one. When you will try to find something about PGO, the default PGO will be a PGO via instrumentation. It's called, like, that's the default one. It's available in all compilers, in all major compilers. And in some compilers, like LLVM, there are several flavors of instrumentation PGO. For example, LLVM has at least 3 common types of instrumentation PGO, which is called front-end PGO, fprofile instr generate flag, IR PGO, fprofile generate flag, and context sensitive PGO. That's I don't remember the exact flag. They are pretty common. They are pretty safe to use from the compiler bugs perspective, but that's okay. The second one is sample-based PGO. It's kind of popular. It was invented by Google. It's kind of popular nowadays, but we will find far less information about it in the internet. And when anyone is talking about PGO, by default it's about sample-based PGO. And also you can find on different forums, usually on an LLVM discourse forum, you will find some uncommon types of PGO. The first one, that's usually it's different kind of modifications of existing PGO modes. For example, context-sensitive sample PGO. They're trying to improve the precision of the gathered PGO profiles, etc., etc. There is an interesting PGO type which is called temporal PGO. It was implemented by Meta, and it aims not improve CPU efficiency of your application, but improve the startup time. And the main goal of implementing this stuff was improving the startup time for application on mobile devices. And also different PGO types, like trying to use PGO not only on CPU. PGO is available at the moment only for CPU stuff, for GPU, something like that, but you need to understand that all of things in the uncommon block, they are uncommon for a reason, because almost no one except the authors use it. And you should expect a lot of bugs, a lot of seg faults in the compiler when you will try to use it. That's a pretty regular situation, and be ready to fix it by yourself or your favorite agent. Since we had so much types of pdraw, so of course it was an obvious situation that several projects in the open source ecosystem will mess with them and will try to use not a good pdraw type. For example, for many years, LLVM Clang pdraw guide was recommending by default front-end pdraw because it was implemented earlier. But it's, according to some benchmarks, I guess from Google, it's less efficient compared to IR pdraw. But the recommendation was still there, and I've only came after 3 years, I guess, and just put this thing in place, and we needed to fix it. That's, I guess, from that's from Yugabyte database, and they just fix it. Okay, that's a good one. But how many projects do we have not an open source ecosystem? Who knows? So let's talk a little bit about how instrumentation pdraw work under the hood. The idea is really simple. At first, you need to compile your application in the instrumentation mode. During this compilation, that's usually fprofile generate flag, the compiler will add additional instructions into your binary to collect some different metrics. And also, it will add a specific runtime, compiler runtime. It will be linked. For example, if you have some tricky CI pipelines and stuff like that, don't forget to link it because you will get some linker errors. So on the next step, you need to run your application on some target workload that's called a pdraw training phase to collect some data. You need to collect these pdraw profiles. The collection process is not that simple because these profiles need to be processed. For LLVM, it's done via LLVM prof data tool, and for GCC, it's done via gcov tool. Of course, each tool has different limitations. For gcov tool, there are some seg faults when you'll try to merge multiple specific profiles. It's not fixed. So be ready. And after you've processed these profiles, you need to recompile your application once again. And this phase is called pdraw optimization phase. And that's it. Actually, you've got your pdraw optimized application. Unfortunately, there are some caveats in this process. At first one, at first you need to compile your application multiple times. The first one is for instrumentation phase, the second one in the optimization phase. It could be a problem for CI, especially when your application is large and you have some limitations on CI. For example, imagine the case of GitHub Actions and some limits on it for open source projects. The situation becomes especially bad when you have multiple stages of pdraw. For example, official Clang recommendation recommends you to run at first step intermediate representation pdraw. After that, you need to apply context-sensitive intermediate representation pdraw. That's free compilations. And also, you can apply post-link time optimization. We'll talk about it a bit later. So you will need to rebuild your application 4 times. It's not fun. And second topic is issue that your application will be larger because an additional amount of instructions is inserted. That's not a big deal, but anyway, and your application will be slower. It could be a problem. So I gathered some data regarding the binary size increase. These benchmarks were done I guess several years ago. They're done by Clang and front-end pdraw. You don't need to focus a lot on these numbers. You just need to get the understanding that the binary size increase would not be a huge problem for you. It could be a problem for some specific domains like embedded stuff, but anyway, in general case, no one cares about it. But about this one, about binary slowdown, the situation becomes much worse because in general you cannot predict how much of slowdown you will get from applying the instrumentation after applying the instrumentation into your application. It depends on the application. It depends on the training workload. And for example, if you had a really hot loop inside your application, and into this loop were inserted these counters, so you will get really great slowdown. For example, it was the ClickHouse case. But in general, just make an experiment and measure it, and that's it. So Google engineers, they met all of these problems like, I guess, 15 years ago, and they decided to implement a new PGO way. Like, it's called sample-based PGO or sampling PGO or feedback-driven optimization. It was invented by Google and out of VDO. So the idea about it is almost the same, but there are some interesting details. At first, instead of rebuilding your application with some instrumentation, you just run your regular application. You need to, instead of instrumentation and adding counters and stuff like that, you just need to provide a little bit more debug information to create some mappings for profiles. Usually it's a -G flag, or also it's also recommended for LLVM a -F debug info for profiling. It's an obvious switch. The second step is you need to collect profiles, like how your application is executed with statistics. But instead of built-in gathering mechanism via instrumentation, you just use an external profiler. Usually it's used Linux perf. That's by the default choice in the industry right now. And also you can try to use Intel VTune or actually any profiler that you have, but will be a caveat in the future about it. And on the next step, you gathered profiles, you need to convert them, because your compiler knows nothing about the format of Linux perf profiles or Intel VTune profiles. You need to convert them. For this stuff, you need some special tools. And for example, these tools need to support your profiler. And here is a caveat about some custom profilers. For example, the existing tools in the industry support only Linux perf, and if you are lucky enough, Intel VTune. And if you have any kind of custom profiler and especially proprietary profiler, be ready to write such tooling by yourself. And the rest is pretty the same. Recompiling, and okay, you got a PGO optimized application once again. Next interesting feature is you will see in different sample PGO guides that there is a thing like a last branch record or branch stack sampling or stuff like that. It's a hardware feature which that for sample-based PGO allows you to gather profiles with higher precision. So more precision in your profiles, better information about how your application is executed. The compiler optimization will have better quality. But this feature has multiple names, and they are not the same because that's a hardware-specific stuff. It's just a keyword to search about it over the internet. You need to understand that this feature, hardware feature, at first is not required for sample-based PGO. Yes, it improves precision, but you still can use sample-based PGO without it. You will get you will miss some optimization opportunities, but how much depends on your application once again. And another important thing that this feature usually is not available in virtualized environments. For example, if you have something cloud-based or whatever else, just forget about it. You will not be able to use it. Bare metal is what you need to use in this case. So let's talk about tooling to convert profiles from profiler format into compiler compatible format. By default, by default, you will find projects like Google out of VDO. That's, for example, is the reason why sample-based PGO is often called out of VDO. You will need to understand the difference. Out of VDO is the name of this tooling, specific tooling, and sample-based PGO is optimization technology. So Google After VDO It's an open source project. You can read it. It supports conversion from Linux pair of profiles to both LLVM and GCC. GCC is an asterisk because several months ago Google decided to remove the GCC support, and because they don't use GCC anymore for many years internally, and they care only about their workloads. And there was a discussion in the GCC mailing list, and as far as I remember, some guys from NVIDIA decided to contribute this support directly into the GCC. So Google After Video also supports working with LBR and non-LBR profiles. That's a good thing. But when you will try to use this project, you will see a lot of interesting problems regarding the compilation stuff. Because this tooling need to use different internal parts of compilers. And for example, about LLVM, we just use a specific LLVM version, and that's it. The issue here is that when you will try to use for a newer LLVM version, of course you will have a lot of compilation issues, and you will need to fix them. That's really not a big deal, but it's pretty annoying. And you can see a lot of interesting pull requests into these projects from a lot of issues about complaints. My build is broken with the recently released LLVM, and multiple PRs about fixing it. Some of them, they are not merged. The second tool is LLVM ProfGen. That's a part of LLVM, so no building issues. No support for anything beyond LLVM, of course. And the biggest limitation here is that it works only with LBR-enabled profiles. I've asked an issue in the upstream about is it possible to add an ability to use non-LBR profiles, and they just said we don't care about this use case. So, okay. And you can write, of course, your custom tooling for your custom use case. So let's do some quick comparison. From the optimization perspective, instrumentation PGO allows to perform more optimization because it can gather more information, like with better precision how your application executed. Is it a big difference for your application or not? You need to benchmark. From runtime overhead perspective during the PGO profile collection process, instrumentation has a big overhead, and the sample-based PGO has really low overhead, like a few percents, and even this amount of overhead can be easily tweaked by the profiling sampling frequency. It's pretty easy. From a tooling perspective support, instrumentation has better tooling support because it was available for many years before sample-based PGO was implemented, and it's has bigger community, I would say. It's not a big community for PGO, but it is what it is. And from platform support, instrumentation has just a better, wider support. For example, once again, MSVC. MSVC just recently added support for sample-based PGO profiling, like in the most recent version on the profile. And for example, if you use Windows and you compile this interesting compiler, just remember the case. And also there are some limitations about the cloud providers and LBR stuff. Instrumentation doesn't have such an issue. So let's talk about the compiler support a little bit more. Well, here the situation is pretty simple. Clang is the best compiler from PGO perspective, not because I'm LLVM fanboy. The reason is that all of the developments, almost all of the developments in the PGO field is done by Google in LLVM, and they care only about LLVM. So that's why all of these technologies and the RFC style, they are implemented in LLVM at first, and later they are propagated to the Clang, and that's it. GCC also has a pretty good PGO support without like fancy PGO mode or whatever, but you will have no need, almost no need to use it in the everyday life. MSVC, and for some custom compilers, but again, MSVC has a pretty good support for instrumentation PGO. You can use it, and it works. It has a kind of interesting stuff that, as far as I remember, you cannot use PGO without enabling LTOR in MSVC compiler, and enabling LTOR for the large C++ project can be a really interesting task, because a lot of interesting ODR violation rules and uncovered undefined behaviors, but it's C++, we like undefined behaviors. And regarding any kind of custom compiler, you need to ask developers directly, for example, some proprietary stuff or whatever else, and just consult with their devs. Well, how C++ is compared to other languages from the PGO perspective? So the situation is pretty easy. C++ is the best here for exactly the same reason that we had in the previous slide, because Google cares mostly about C++ stuff, and they implement it. That's why all of the things are available in Clang, and even if usually, like nowadays, all of the development about PGO infrastructure, they implemented inside LLVM, and all the things you need to implement on the front-end part of the compiler just add switches and some stuff, some propagation stuff. It's not a big deal, but anyway, it's done only for Clang. C++ has really good support from the compiler support documentation. C++ compilers has the best documentation about PGO, and from the community experience, like if you will find any kind of PGO guide with high probability about C++. Other LLVM-based languages like Rust has worse support, but there are some interesting stuff anyway. For example, Rust doesn't support sampling PGO in the Rust stable. My pull request is not merged for months. Go supports only sample-based PGO, because Go was implemented like later than C++ and was implemented by Google, and Google uses only sample-based PGO, and they don't care about instrumentation internally. Like different technologies like Java, in Java there is a project like graalvm for ahead-of-time compilation model. In C# there is an interesting thing that is called dynamic PGO. It's kind of combination of just-in-time and ahead-of-time worlds from PGO perspective. And for other technologies, with high probability, PGO will not be implemented, because if they have a custom compiler, they will need to implement all of this PGO stuff internally. So that's not an easy task. So if you will try to learn something about PGO, not only from C++ world, you can check these technologies and their recommendations. For example, the Go compiler has a pretty good guide about sample-based PGO, and interesting detail, it's based on a pprof profiling platform. So if you use pprof internally, you can take some inspiration there. C++ tries to be modern, so we have a pretty good diversity here. And as you know, we have a lot of build systems. We have a lot of ways to manage our dependencies. That's are screenshots from the state of the C++ ecosystem 2025 from JetBrains. So, and this situation is creates an additional amount of problems for us, because from the build system support, from build system perspective, you will see almost no help or helpers for enabling PGO stuff. CMake, no support. Bazel, some basic support, I guess, but who cares about Bazel beyond Google? Meson has some support for PGO, but it's available only for GCC, and for LLVM there is an open pull request for several months. So no support. Also, since you have no support, you will see some interesting issues. For example, when you will try to enable PGO and you had already enabled a warnings as errors policy, PGO will introduce additional amount of warnings into your builds, and of course your build will fail, and you will need to tweak all of your scripts, build scripts. You just need to be ready for that. Interesting story about dependency managers. If you use it, like Con and VC package or whatever else, they also don't have helpers, and it creates interesting things that if you have dependency which are managed by dependency managers, you need to spend additional amount of time to propagate, like for PGO training and optimization phases, into building all of these dependencies too, because if your flags in your build scripts are not easily propagated, you can have like really arcane trickery in your build scripts. I've met it almost at any place where I've been working. And from this perspective, it's really much easier to enable PGO for dependencies if they are like a part of your source tree. That's a pity situation. And as a rule of thumb, you should expect that nothing is PGO optimized, and you need to rebuild it by yourself. For example, from the previous talk, there was FLTK. FLTK was a part of system dependency manager. Of course, it's not optimized by PGO for your specific Pomodoro Pro Ultra Fast. How to integrate PGO into build scripts? So usually we'll see the following pattern. Of course, the first one and the most popular one, no PGO. So, but if you want to integrate it, you will see by default a lot of bash trickery. It's what will be generated by AI by default. Some Python scripts for managing PGO flags. For example, you can see in LLVM project, you can see some bunch of CMake scripts for training PGO for Clang and other LLVM tools. And in some really advanced cases, you can find in the ecosystem some stuff like optdis tool. That's a dedicated tool to optimize the RAS-C compiler on the CI part. I've never seen anything like that in C++ world, but we take an inspiration there. That's pretty good tool, to be honest. So let's talk a little bit about reproducible builds. Reproducible builds are a hot topic nowadays, especially in open source world. And here here we have two cases. The first one, if you already had a reproducible build and you want to apply PGO optimization. The best, I guess the only way here, you just collect your PGO profile, save it somewhere, and use it during each compilation for your reproducible builds, and your build will stay reproducible. You will create, as soon as you save the profile, you will create additional problems that you need to update this profile, you need to manage somehow storage of it, but that's another story. And the second question is, multiple people ask me about reproducible collection of PGO profile. So you run your training, you run your training workload, and you want to get the same PGO profile during each training phase. It's just an impossible task to achieve. There are multiple reasons, because applications are executed in different ways, blah, blah, blah. And there are multiple issues with that. For example, it was the answer of one of the developers of a PGO compiler, of PGO infra in LLVM, like atomic stuff inside or whatever else. So it's just not possible in real life. You can, by default, in instrumentation PGO, the profiles are saved to a disk after the exit of your application during the training phase. It's pretty okay in most cases, but you can tweak this behavior. For example, for LLVM, there are multiple ways to tweak it. For some pretty easy tweaks, you can use LLVM profile file environment variable with some specifics, like for some custom path with some modifiers. And the advanced things are via compiler-specific intrinsics. This way is available for all major compilers. For LLVM is a bit easier to use it, but it's a part of compiler runtime which is linked. And you can use the same thing like underscore LLVM profile dump or something like that. For GCC it's available too, but a bit more complicated to use. For MSVC I don't remember. And of course all of this stuff is not documented at all, and you will need to read compiler sources to use it properly. Luckily there are some comments inside sources. And as an example, you will see in multiple projects, I guess it's from Yugabyte too, this implementation could look like that. Here we have just a dedicated thread, and in this thread, all of these profiles are regularly dumped to a disk. So it's, by the way, it's a useful thing because if you had a training session for multiple hours and your application just faulted at the edX, you will miss all of your profiles. Not a good situation. I've been there multiple times. So about like environment-specific tweaks, there are some percent blah blah blah. It's not interesting stuff. You can read it, but you need to be careful here because, of course, all of these tools, especially fancy flags like %C, that's a continuous saving mode. It's buggy. It's buggy. It has specific bugs on specific platforms. And of course, you can try to find some issues in the issue tracker. There will be no activity there, and it's just real life. So if you want to use, if you want to try, you have a large fleet of application. For example, you are Yandex, yeah, and you have a lot of application to optimize. You don't want to optimize all of them manually, and you want some kind of platform that will try to do all of these optimizations for you in some at least semi-automatic way. Initially, it was implemented again by Google. Internally, it's called Google Wide Profiler, GWP. It's not available to use. We just publish a paper about it, and that's it. Based on this paper was implemented Yandex Perforator. And it's right now the only available solution for C++ world to apply continuous sample-based PGO. There are, for example, for Go is also available Parka platform, but Parka doesn't support C++. So Yandex Perforator is the only open source, good license, highly recommend to use it. It's possible to implement all of these things based on our platforms, like, for example, Grafana Pyroscope or Elastic Universal Profiling. But I've created issue there, and I guess for several years, no activity there. So they're just not interested in it. But they said, yeah, we're interested, and that's it. And of course, if you have such kind of proprietary platform, for example, like Ozone, you can Ozone Vision, you can try to implement it it's internally too. That's how Ozone did. And remember that even if Yandex Perforator is, well, it's the only solution, it has some kind of limitations. Like, for example, that's a screenshot from their documentation, only officially supported only LVM toolchain. You need to specify like additional debug profiling, and you see some interesting stuff like last branch record requirement. Let's remember the bare metal world. Okay. Quick few words how to collect PGO profiles. There are actually multiple strategies, but at first, let's start from about unit tests. Please don't collect PGO profiles from unit tests during the training phase, because unit tests usually testing corner cases, and corner cases is not your target workload. I hope so. So the benchmarks actually is pretty good way, but it depends how real your bench suite is and how it's compared to real workload. For example, for databases, it could be a pretty good approach. It was, I've tested it multiple times, but it depends on the bench suite once again. One of the most popular way in open source nowadays is manually crafted training scenarios. You will create some bash script, and it will implement some kind of different training phases. For example, for Clang, it's just compiling the Clang itself. And for the Rust compiler, it's just compiling multiple most commonly used libraries. And that's it. That's pretty good. But you need to remember that in this case, you need to maintain training scenarios. You need to track that your training scenarios are pretty comparable to real workloads, and it's not suitable for all cases. For example, server-like workloads, which can be pretty dynamic. And gathering profiles from production, that's really the greatest option. That's, for example, how sample-based PGO usually used in some large companies like Google, Yandex. But this option is also not ideal because it's a production environment. You will get additional amount of questions from security guys, for example, what are trying to collect, and you need to think about it. Also, some kind of overhead. Remember it. So, also, you will when you will try to find some information about PGO, you will also find a thing that is called post-link optimization, or PLO. PLO, that's additional interesting optimization that actually tries to optimize the binary layout of your application, to optimize the CPU instruction cache utilization, because so frequently called functions together, that's a clever idea to put them in the binary at the same place near, so your CPU will be happy. But they actually do much more. The default tool for PLO nowadays is Bolt. So right now it's LLVM Bolt, so the part of LLVM, no compilation issues, luckily. Also you will see tools like Google Propeller and Intel TLO. Intel TLO is already archived during the recent Intel cost-cutting activities. Google Propeller is less tested, but it should be okay too. Workflow is pretty the same as PGO. There is instrumentation mode, there is a sampling mode, at least for LLVM Bolt. But this PLO can achieve even more optimizations even after applying PGO, because it implements some additional amount of optimizations. But you need to remember that PLO is a much newer tool, new approach to optimize, and it has a lot of bugs. It just has so much bugs. It has limitations like really limited architecture support. For example, right now LLVM Bolt is mostly tested only for x64. I guess no good ARM support, or like maybe some architectures like Elbrus. Well, a lot of bugs, of course, really big instrumentation. For example, if you will try to use LLVM Bolt via instrumentation, it has a much bigger runtime overhead compared to PGO. There are a lot of interesting issues there, but I need a dedicated talk about it. And for example, that's why, since that's a new optimization approach, if you want to get really advanced optimization pipeline, you need to use all the things together. For example, that's a screenshot from Cache OS, one of the maintainers, and they try to apply all of this stuff for the Linux kernel. And of course, since there are a lot of stuff, a lot of unstable stuff at the same place, of course, you will get some sick faults. And that's it. They just decided not to deliver this optimization pipeline. But it's possible. But it's possible to use. You can play with it. But please be ready. And for example, that's a demonstration of Bolt benefits, even then Bolt is applied after PGO. That's talk was from Amir Ayupov. Amir Ayupov is one of the developers of Bolt, so he has some articles about it, so you can Google it about it later more. So that's useful stuff. So, and to conclude my talk, of course, I've created a lot of PGO issues on GitHub. If you will try to find something, I'm kind of PGO spammer. Several people tried to ban my GitHub account for that, and they were not lucky. And I had a lot of interesting discussions, and it was a discussion with, I don't remember the name, Gerhard. It's author of RCSlog. And I've applied PGO to the RCSlog to improve performance of log pipeline. And I've got some performance improvement in my bench cases. And the end of the talk was like, well, you know, it's like some compiler tricks. I will better spend more time on optimization algorithms instead of compiler tricks. But the real thing here is that you don't need to choose. You can optimize algorithms, and later you can optimize your optimized algorithms with some data-specific stuff, which what PGO actually is in practice. So, good candidates to apply PGO. There are actually any kind of software with a lot of branches and a lot of different workloads. I have in Awesome PGO, I have open source project which is called Awesome PGO. The link will be later, where I have benchmark for a lot of stuff from different domains, game dev, compilers, databases, even operating systems like Linux has official support for building with PGO, with sample-based PGO, contributed by Google, of course. And so you can try to optimize any stuff like that. And for example, there are some papers about making application-specific operating systems when you build a specific Linux kernel only for running specific applications, where you tune so much. And so awesome PGO link. If you want to read something much more about PGO, I've tried to collect there as much material as I can, because I need to create a workshop to put all of this stuff at one place. And you can ask me whatever you want, question. So catch me if you can somewhere. And that's it. Thank you.
Alexander, thank you very much for a brilliant talk. I just wanted to say that our conference is such a danger place, because I nearly caught your addiction to PGO. And I think some of our audience also could cause this addiction. Please raise hands who want to test PGO in your own project. Wow, great.
At least someone. Who didn't
raise a hand is in danger, because of Alex will remember you and we will reach out to you.
Yeah, you can talk to him on the break.
I like how he reached out to Miloš, our first speaker. Fortunately, he is the second one, because otherwise he would reach out to everyone.
Yeah, actually, yeah.
But he will.
Yeah, I'll try.
Okay, yeah, Evgeny, what about you? Do you want to test PGO?
He already tested it, because we had a discussion on GitHub, and your latest comment was that the proposed bench suit by me, they are not good enough, and that's it. But I provided benchmarks, yeah.
Great.
That's like kind of personal.
Okay, no, our problem, I mean, that's about us. We really want to use PGO, but Alex mentioned two types of compilation: ahead of time and just-in-time compilation. And we have another one, actually, and it's a very popular model. It's out-of-time compilation. So we are usually out of time, and it's complicated for us to use PGO. So do we have any questions? I believe we should have a lot of ones.
Hello, thank you for the talk. It was extremely useful. Yeah, everyone now has a lot of homework to do. But I had a question about maintenance of vendor dependencies and like your specific problem when you try to integrate it. Are we talking here about some global flags, or do you need to like play with build scripts of your dependencies pretty like massively, I guess, that you need to abandon standard package managers? Because, sorry, just quickly for context, because specifically for Conan, because it rebuilds build systems, you kind of can avoid this problem when you have these tricky dependencies with like strange like branches for build flags and all of this stuff. And you could provide like global set of build flags and linker flags for your whole dependency tree, right? Yes.
Yes. So actually, we have dependency management based on Conan. We have a wrapper above Conan, and the real stuff is, yeah, you can provide some global flags, and that's the way. But the real issue is that like you have an additional layer of fuckery, I would say, where the maintainers of the package recipe can decide to overwrite your flags somehow, and you find all of these things just randomly because, for example, one of your dependency wasn't optimized, and you need to figure out why it was the case. And for example, when you try to apply global flags or in whatever way, you will not go to the generated assembly and just see that the binary was changed and was optimized by PGO, because it's not real in practice for large applications. That's why, for example, as more abstractions above the code and of building it you have, the more layers of failing you have. That was my idea, but it's completely possible to provide global flags or whatever the way, and it's actually the best way.
Thank you.
Yep. So, is there any reports of using eBPF to add instrument-based?
Yandex Perforator uses eBPF for gathering profiles internally.
Okay.
I guess that's why we have a requirement for Linux kernel 5.7 plus.
Yep. Thanks.
Okay, my question, if I may. It's here.
Okay.
When we add this overhead to collect the profile, can it change the hot path of the program compared to a clean release build and hide the place that we actually need to optimize?
Well, in theory, yes. For example, the obvious case, for example, you have some time-based logic and based on your execution time, for example, game, and you have like a hard budget for the frame, and depends on that, you change some kind of logic, for example, like rendering pipeline, something like that. It can be changed, yes. But in practice, it will not, because, for example, well, when we are talking about instrumentation, so the additional amount of instrumentation code is added and your application is still executed on the same code paths, but slower. But it will execute when during each time when you go to the branch or to the function, the counter just incremented. So the the result of hot paths that was gathered by these metrics will not be changed. But for some applications, like I've said earlier, it could be the case, yeah.
I have a question about profiles and whether we can reuse existing profiles for different builds. Like we changed code, can we build profile once a week and reuse them during the week to build other builds?
Oh, that's a really complicated topic. So let's start from the basics. The rule of thumb is that you need to use as close as possible profile, and ideally for each commit, but that's not the real deal. For example, the real part, you just need to rebuild PGO profile for each release, for example, and if you release each month, you just once a month run the PGO profile gathering. So if you want to do some kind of PGO reuse profile, it's possible. For example, you gathered a PGO profile and you added some sources. You just write some bunch of code. So the new code will not be covered by PGO profile. It will not be PGO optimized, by the rest of the code will be PGO optimized. And that's it. You will possibly you will miss some kind of optimizations, but that's not a big deal usually. But if you change the hot path of your application, it could be a big deal. So next thing is when you will try to tweak compiler flags. Here the situation is pretty simple. As soon as you will try to change any compiler flag, instrumentation PGO profile almost immediately will be fully invalidated. For example, you changed 02 to 03, different optimization passes are used internally by the compiler. You will see you can get some metrics to compare PGO profiles. So you will get 0% overlap. You've enabled LTO, 0% overlap. You've changed compiler version, 0% overlap, stuff like that. So just use as fresh as possible, as fresh PGO profile as you can.
Well, at least it doesn't crash. It's good.
Well, sometimes it could be the case because no one actually heavily tries to test using really old PGO gathered profiles with a new compiler, stuff like that. I guess I've seen several bugs like that in the LLVM issue tracker, but no one cares about it.
Yeah, thank you.
That's the first time I see Alex saying ouch. That was a nice question. Maybe you have more questions to grill him more? Call me to have a look, please.
Maybe you already told about, maybe I missed this topic, but the question is, did you try to investigate what really happens under the hood when you enable the PGO? Because I see that from candidate list, when you recommend to use PGO, here's a lot of like parsers, database things. It seems like there is a lot of IO operations.
No. That's, for example, for compiler, there are not so much I/O operations, and that's a CPU intensive. For example, for databases, of course, I'm talking about a CPU part of the workload in databases, because it could be kind of heavy, and that's why, for example, PGO works pretty well for databases, but I/O is not optimized at all. So what is optimized? Actually, the first one is inlining. So compiler changes inlining decisions. So in cold places, no inlining happens, and it doesn't blow up your additionally, for example, instruction cache. Hot-cold code splitting is done much better. Branch reordering is done based on the runtime statistics about which branches are executed more frequently. They are reordered, that the hot branches are moved to the earlier into the function. You can see some tricky code splitting stuff based on the runtime part. Interesting thing about LTO and PGO relationships, because so there is a fat LTO and thin LTO. Thin LTO, just a fat LTO which is split into several parts. Thin LTO, so the part that is PGO optimized in thin LTO is this splitting, because based on information how your application is executed, thin LTO can decide based on this data how to split in a better way into these parallel optimization modules, I would say. I don't remember how they call properly. Is it useful in practice? No benchmarks is available. I've asked the thin LTO developers on the LLVM forum, they haven't shared it. But they just answered, yes, it could be improved. Is it useful? Who knows? We need some benchmarks. So stuff like that.
Thanks.
Hello again.
Yep.
Those PGO include things like self-modifying executable, as in it's modifying its bytecode in runtime.
Well, modifying, so PGO is not applying to this kind of like self-modifying stuff, because maybe it's possible, but it's mostly like a just-in-time compilation model about self-modifying something like that. We don't have much in C++ like that, but in general, PGO has nothing with self-modifying stuff. You just, during the training phase, gathered profiles, save them to somewhere, then pass to the compiler on your CI during the PGO optimization phase, and that is. So when your binary is PGO optimized, so no stuff like self-modification in runtime is done. It's just a better optimization based on date of execution, and that's it. So the rest of the optimization pipeline and the rest of the optimization which are done by the compiler is the same.
Thank you.
Hello, thank you for the talk. It came to my mind that first thing I would like to optimize is OpenCV library, but then I remembered that OpenCV builds different function versions for every CPU vectorization method, so it will be most likely impossible to gather profiling for all of them. We'll just get one, and the rest will not be covered, and most likely the build that will be kind of optimized will not be really optimized on some other device.
Well, I have a recommendation here that's kind of strange to hear from me, but OpenCV is a bad candidate to optimize with PGO. Why? Because PGO really shines in large applications which are not a lot of tricky branches and stuff like that, and where humans or AI or whatever else haven't spent much time on optimization. In OpenCV, most of the hot stuff is already heavily hand optimized, for example, by some like CPU stuff, like runtime CPU dispatching and stuff like that. And for example, it's no reason to apply PGO. You can try, but you will get, I guess, almost no improvements. And for example, the same case for FFmpeg, for example. It's heavily assembly level optimized, and PGO can try to make even thing worse. By the way, if you have inline assembly, it will not be touched by PGO because compilers are actually pretty shy when they see inline assembly and will don't try to perform some tricky optimizations. About your question, for example, if you have such part of the application where you have such type of dispatching, the best way is that you need to gather PGO profiles on each platform, because on different platforms you have different macros they will try and they will open in different ways. And for large applications, it's really hard to predict how all of these things will open and how the profiles across multiple platforms, for example, will be common. How much of the things will be in common.
Thank you very much.
Так, дорогие друзья, давайте последний вопрос. К сожалению, немножко выбиваемся из тайминга.
Thanks a lot. You mentioned about UB.
Yes, I can without a microphone, but I can.
Так, мы должны в трансляции тоже услышать вопрос, поэтому...
I will repeat.
Okay, got it.
Okay.
You mentioned about UB exploitation and the most lovely thing in C++. And what's about UB exploitation and optimization? We could use UB, and after the optimization, we have another UB.
I've just referenced UB stuff in C++ from the LTO stuff because that's where enabling LTO fails, and I personally recommend try to enable LTO before applying PGO because enabling LTO in general case is just one compiler switch, and it's much easier to enable compared to PGO. You've seen a lot of the things that should be changed in the CI pipelines. For example, YDB use case, we've still not implemented it. But from PGO and UB relations, you should not expect any kind of additionally uncovered undefined behaviors after applying PGO, because it's just mostly different inlining and just branch reordering or whatever else. It doesn't change optimization pipeline so much as LTO does. So LTO starts to optimize across multiple translation units, and since we have ODR rule in C++, it brings really messy stuff. But LTO is just like a big change to the optimization pipeline inside the compiler. PGO is a more local one. It's still useful, and if you've seen a lot of benchmark, but that's a local change. And that's the reason why PGO does not uncover more UB in general.
Thanks.
Alex, could you please open a very important slide with QR code? So now everybody, please take your phones. We're out of time, so please take your phones rapidly. I count you. And Alex counts on you.
Yep.
Alexander, thank you very much for answering all questions and for so brilliant speech.
Thank you.
На этом наша утренняя сессия завершается, и сейчас есть две очень важных активности. Одна из них обед, а вторая это робот-рейсинг.
The talk is indeed was very addictive, so it's rehab time. Please enjoy your lunch. It's served in front of the audience. And also feel free to reach out to Terrace. It's across from the office entrance. But don't forget to come back at 1:40.
Очень Дорогие друзья, мы рады приветствовать всех снова в этом зале нашей конференции. Я очень надеюсь, что вы все хорошо отдохнули, хорошо подкрепились, потому что сейчас нас ждет, на мой взгляд, один из самых интересных докладов, который расскажет нам про самую восхитительную возможность будущего, именно не такого далекого будущего, C++ 26, и это сделает Душан. Чуть об этом рассказе на английском скажет Женя.
Welcome back, everyone. I hope you had a great lunch and ready for new hot stuff, because the stuff is really hot. We are going to listen to Dusan Jovanovic. He will speak about reflection. It's a cool topic. It's a new stuff. It's a hot stuff. It's I always reflect about why I don't know anything about reflection, but things will change right now. So reflection is a very anticipated feature of C++ 26, and there are a lot of discussions how and what. And I hope that Dusan will tell us a lot about reflection, about applications, about JSON and YAML applications, and how you can do reflection compile time to have to get a really great stuff compile time. Dusan, please welcome to the stage.
Thank you. Just take the clicker and check. Okay, great.
It's time to hide for us.
Thank you. So before we start, can I see like a raise of hands of how many people already saw what C++ 26 reflection looks like? Okay, so this joke in the title might miss a bit, but as we've seen, missing jokes is not a problem on this stage. Okay, so a little bit about myself. My name is Dusan. I'm president of C++ Serbia user group. We do monthly talks, so each month you can look for us and you'll find talks. Not like this, a bit more chill, but yeah. I also work as a co-CTO at Inceptive. I've been using C++ for 20 years, and in my company, the current standard that we use is as close to C++ 26 as we can. This code right here is something that everybody wants to be executed, right? When we write C++ code, we want to deal with business logic. We're creating some applications. We want to write our types. We want to instantiate our objects. And we want a lot of stuff to work. We don't ideally want to write code that will print our custom type every time we instantiate it. But the problem is that that code needs to exist somewhere. So it's not like it's going to magically print out, because in memory, your data is stored in binary, and you want it to be printed out very nicely on the output. So that code to manipulate bytes to switch from your types into text that's representable on the output and be human readable needs to exist. The problem is only who will write this code and at what point. So we can either write it ourselves, right? Every time when we have a new type, or we change a new type, or we want to add new types of formats that we support for our types.
Dusan, I'm sorry, could you please hold your microphone closer?
Yeah, okay. We can do it like that, but this is not what we want to do. We can create an external tool that we can run, and it will generate new code for us. But as you've seen with PGO as well, adding stuff into your tool chain is tedious. Also, when you're writing this new tool to write your C++ code, that tool doesn't know C++. So you need to teach it to generate valid C++. It also, when you're defining your types, you're usually using a language, like a specific format to define your types. So it's another language to learn, another runtime to run inside your builds. And so when I was dealing with this problem, these two approaches weren't very nice to me. So I decided that the ideal way to do it is by using the C++ compiler. C++ compiler knows what C++ looks like, knows how to deal with C++ types. And ideally, we write this serialization once, and it works for every type that we have in our code base. And the fact of the matter is the title of the presentation is a bit false. Like, you don't delete the boilerplate, you just stop typing it. In our case, this year, generating it with AI, but yeah, it still exists. It's just materialized somewhere else. So here is where C++ reflection comes in and solves these problems. It's a tool that we can use to solve the problem of serializing our types generically. And it does it using two mechanisms. One mechanism is the introspection mechanism, where that's the part where the compiler asks things about your type and discovers things about your type. So you can ask questions like, what are the fields of this struct? Or you can inquire about the name, capture all these as values, and then use them in the next step, and that is code generation. Code generation takes all of this information that we captured in the previous step, and then it can generate code for us. It can be code for serializing the data, but it can also be code for building new data types. In this presentation, we will focus on the first use case. So generating the code that will write out our types and read from other sources and populate the data in our types. So this is a whole new feature. It's a new layer on top of templates. Templates were the C++ thing to write the generic code. Before that, in C, we had macros. And C++26 reflection is another layer that will allow us to generate even more generic code than before. So before we go and see how C++26 reflection looks like, I just want us all to agree that there is a problem of writing this code, right? I really want to show you what we would have to write if we weren't doing it in a generic way. And I'm guessing a lot of you have already seen code like this, because everybody in their code has some enum. You are working with your enums, and then you want to write out your enums, let's say for logs, or sending it through to another API. So here you define your enum. Let's say here we are customizing it, the formatter, the std format API to write out the types, our enum type on the standard output. So in C++, you do it by defining your enum, filling out this template of formatter, and then you have some code like this, right? And if we take a look at this code, it's highly repetitive. Here you have this home, and then home repeated again, and then some code around it. But you're basically, what you're saying is, my enum home needs to be printed out as string home, and my enum work needs to be printed out as string work. And you have a lot of code around it that you need to write in order to achieve this. And you need to write it again. So when you have your email struct type, you repeat this just for the type. So what you do is now you're forming your type field, and then you're printing it out, and then your email field, and then printing it out. This type works because we implemented the enum part before, right? And then we write it again for our user. So we have this user struct, and then we again have to write this again. Make sure to remember this comma, because when you're dealing with enumeration and arrays, the comma shouldn't be at the end. So we need to pay close attention to handle this properly. And this is really tedious. We would have to do it for every collection in our code base. And that's not very nice. And then we will write this again and again for every other type in our code base and for every other serialization type. So here we're printing it out on the standard output, but we also work with config files. Config files are some YAML files. We need to implement serialization and deserialization from YAML. We have JSONs on our APIs, so we also write JSON serialization. Then we need to store our types to the database, right? Because we're writing backend code here in back-to-back. So we also need SQL serialization. And our app takes some CLI arguments, and why not serialize them as well, right? When you're reading your CLI arguments into memory, it's also some kind of deserialization, right? And we need to write this manually, not just once when we implement our functionality, but even when adding new stuff. So if we add a new field to our struct, we need to update this. And we also need to update the test code, which is really important. As we saw previously with that comma, we might have forgotten to do that, but we need tests to make sure that we are respecting our serialization format, because we need to output standard JSONs. So we would need to write tests as well. And on each change, you update the code, but also you update the tests to make sure that everything is running correctly and up to spec. And if you forget to add any of this, you just get a silent failure. Nobody notices. So you added a new field to a struct. This struct now doesn't serialize properly. Let's say you have a save game file you need to load. Now you're not loading this new feature. You're not storing it into your save game. You're not loading from it. So that's bad. And in my company for 2 years, we wrote code like this. And at some point, we were like, it's enough. And we implemented serialization using reflection with the old C++ tricks. And when I say C++, you know it means macros. In 2022, I did, and that's 4 years ago, I did a talk in our local meetup about this technique. We open sourced part of our code base to show how this can be done. So I did a talk, and that library is still live now on GitHub. You'll get the URL for the repo so you can check out the code. And that toy example supported YAML, JSON, and CLI arguments. In our internal implementation, we also support other serialization types as well. And it was built using lots of macros. And this year, as soon as C++ 26 came out and was ready to be used, I took the compiler and ported that library to C++ 26. And basically, this whole presentation came from this. I really wanted to show you guys how everything can be better and inspire you guys to do so in your code base. So a quick overview of what the library from 2022 looked like. So it had this intro gen metadata macro, which is used to add meta information. That's the first part of the whole reflection process, the introspection part. into your struct. So this macro generates lots of code that our reflection library can use. Here, the problem is you need to place every field of your struct into this macro. So we're not solving those silent failures. You still need to update something, but now you're just adding a name to the list. And usually people remember to do that. The next part is that code generation part. And it's done using this for each field function. There are a lot of other functions, as you will see in reflection spec when we get to it. But this one is really important for serialization. Because how serialization works, for each field, you write it out somewhere, right? You change the format, you manipulate the fields and the data. And as you can see, it has the name, and you get the reference to the field, and then you can either serialize it or deserialize it, depending on what you're doing. And you're iterating with this. It will go deep into your struct. And this is the mechanism even C++26 reflection uses, but with a nicer syntax. And with this, we were able to write JSON, YAML, CLI, and even REST CRUD, so auto-generate CRUD operations for any type that is coming into the API using this gen metadata stuff and for each field. And here is how the code gets used. Of course, we didn't write any of the serialization libraries. We just used our reflection library to hook into the mechanisms of existing libraries. So for JSON, we were using Lochman library, and you just write this, like get config, and the JSON serialization was implemented generically somewhere as a part of our library. And the same thing for YAML. This YAML CPP library supports reading from a config file, and you can see it just works. And that intro gen metadata is the only thing that we needed to add to our config type, so this works. We also were using this CLI 11, really nice CLI library for C++ to add the CLI flag support. And for CRUD, we were using Pistache. But the engine behind it all is basically this pretty function. This basically generates, writes out the name of your function as a string. And then we parse it in constexpr to extract all the properties like type, like field names, stuff like this. But you still, like I mentioned, you still have this problem of needing to add into the list. And this is where C++26 comes in and allows us to not care about this anymore. And now I'll show you what was voted into the standard. So we have some new operators, some new functions, and all of them provide us with the mechanisms we need to implement this serialization and deserialization. So we have this reflect operator that turns code into meta info. We have the splice operator that it functions like a pointer, dereferencing, where it moves meta info into code. We have some query functions, and we'll go through these more in detail for you to see how they work. So, first one is the reflect operator. This is something that our library couldn't do. So this is a new language operator. It's read out like double caret operator, but its name is reflect operator. And it turns something into this meta info. You can capture stuff and then pass it around. You can put it in a vector, and it works on anything, and it's a value. what you get at the end is just a value. So you can use it like any other value in your code base. So you can use it on a type. You can use it on your type. You can use it on standard types. You can use it on a property. You can use it on a function. You can even use it on a namespace. What you can do with it is call the standard functions that work with these types. And this was done. So it's like an opaque value. It's like void or void star. You just have it. You yourself don't know what to do with it. You can just call functions that do know. And those are left to the compiler to decide, which is a really great design if you think about it. And it was a big motivation for the committee to add this interface because the API is flexible and it allows you to capture the info from this metadata and then just bundle them all together and write the generic code that works only with this type. As they are values, you can just put them in a vector, and you know, like everything can be bundled together very nicely. This is the splice expression. It's not an operator, it's an expression. Here, you're using the reflect operator to get the meta info, and then splice kind of works like if reflect operator is dereferencing, address capture, this is dereferencing, right? So you can treat them like ampersand and star, right? One does one and the other does reverse. So you'll see it in an example and all of it will make much more sense. Then we have this non-static data member of function. There are a lot of queries, we'll see them all, but this one is important because you've already seen it. This one is the parallel to our for each field function from the meta library. And what it does is it returns a range of std meta infos from your whatever the thing is that you pass it. It can be a namespace, so you can iterate through all the meta info from your namespace. So if you have two functions in a namespace and a type, you get a range which will contain 3 meta infos, 2 for your functions and 1 for your type. But we use it here to iterate through all the members of our struct, right? The important thing is this access qualifier, access context. This tells the compiler to return all of them, so all your private and public information. And the important thing about all of these query functions is that they are all const-eval. So, like the previous metadata stuff and capturing, reflecting, that works in any context, these all work only in const-eval. And there's a lot of them. We are going to use most of these here to implement our serialization and deserialization, but there are more that are voted into standard, and you can expect even more to come. But the first one is the identifier of. All of these are in std meta namespace, by the way. So std meta identifier of gives us a name of the identifier that we captured. Enumerators of returns us a range of all enum meta information. Type of returns the type. Parent of returns a parent of the base class or the base class. And has annotations of is a really cool one that we're going to see later. And basically what they return is a string view. And string views, as you all know, are const-eval, so you can work with them like any string view. So, I mentioned annotations, and annotations are really cool. They are a separate proposal paper, but the proposal paper is called Annotations for Reflections. So these are meant to be used with reflection. It's a new syntax. I'm showing it here. This annotation expression, you basically take a value, so not a type, a value, and you attach it to this property or to your type, and it gets stored in that std meta info. So what you can do is you can ask the compiler using this query has annotation if your type has this annotation. So here I'm giving an example of how we use it, so you don't want to write out the password into the standard output, right? So we use this skip, we define this skip annotation somewhere, we use it on our type, and in our serialization code where we are generating code to print something to the standard output, we're basically asking, oh, does this type have this skip? And if it has skip, we just skip writing it onto the standard output. So we use this to customize the behavior of our generic algorithms. And it's a really powerful feature. This is something that we also have in our reflections library, so I was really happy that this was voted in. As I mentioned, that query that returns the members of our struct is, it returns a range. And here we need to iterate through this range, and there is this new template for expression. If you've worked with macros, it does basically that. It does nothing smart, it just repeats your loop for every member of the range. It kind of works like loop unrolling. And that's it. So let's solve printing enums for all the types that we are ever gonna have in our code base, right? This code here is works for any enum. As you can see, we restrict it to isEnum. We use this template for to loop through enumerators of our enum type. We check to see if the specific value equals to the splice operator. Here it's used to dereference this EV that we're iterating through to match it. And then we just write it out using this identifier of. And this code you write somewhere in a header file. You include this header file in like a big compilation unit that gets included everywhere, and you can print out any enum in your code base. And what is important, that it solved that addition type, a bug that we had. So if you add a new enum, a record into your enum, everything works. Your enum gets printed correctly. And this is something that we finally got in C++26. For all other serializations, the loop will look something like this. You're gonna have your template for, you're gonna iterate through non-static data members of something, and you will capture the name, capture the value, and do your serialization and deserialization. And this is basically it, right? So to repeat, we are going through all the members. We are capturing the identifier of, that's the name. We're capturing the value. And this is how we generate our deserialization. And I'll show it on a primitive example, right? But if you take a look, it's really powerful. So let's say we have some serialization that looks like this. Name of the property equals value. And here I defined a custom function And basically, we have this non-static data members off, and then we print out the name, and then we print out the value, and that's it. And this will work for any aggregate type in our code base. It wouldn't be a nice serialization, right? Because what it is doing is it's basically writing these equal signs, and for nested types, this is gonna look bad, right? But I'm showing you to see how easy it is to write something like this. So let's see how I was able to replace our custom library code with C++26 reflections. Here, hope it's visible for everybody. You have two versions of customizing the JSON library to print out any type. And I'll point you guys to some key differences. One is on which objects we are able to do this. In the C++26 version, let's see if this works, it works. We can do it on any aggregate, right? And in our libraries version, we required that the object was annotated using our custom macro. That's one. Next is we used to use this for each element. Here we use a template for. But this code here and this code here kind of does the same thing. So the mapping, the porting to C++26 reflections really went easy for this one. And now finally, we get to see how that print looks like from the first slide. Now that we have generic JSON serialization for all of the objects in our code base, we can just write out the JSON on the standard output. The good thing about all of this is you probably won't even need to write this, like this code. There are library authors who are doing stuff with C++26 reflection in their libraries, and they are going to be the ones writing this for you, and you're just going to use it. So yeah, printing any aggregate as JSON now just works. And works for any type in our code base, right? And it still follows the same, like it just reuses what we implemented generically. Parsing JSONs is basically the same. We have this, again, this pattern of for loop, and then this, assigning to an object. But the interesting thing is here, right? So what happens if we are missing a field? Well, here we just ignore it, and that's the author's decision, so to say. But in your code base, you can decide what to do here. You can throw an exception, you can return an error, depending on your code. And we can even improve this with annotations, so to customize behavior. So we can say for this type, by default, we can ignore it, but for this type, it's really important that all the fields are present, or this field is present. And you can play around with this to customize the behavior in your code. This was my favorite serialization, by the way, the CLI one, so I decided to show it as well, even though it follows the same shape of for every aggregate, we have this template for, and we deserialize our object using these dots, right? So if we have our config, and we have an endpoint in our config, so we can just say -- listen on dot hostname dot port, right? And it works for any app, makes the CLI code much cleaner when you're writing it. It's not POSIX compliant, but in our internal code base, we don't care. But the good thing is that you don't have to write your CLI arguments. They're just your struct. They automatically get loaded, they automatically get parsed, which is really nice. This is the real win we got compared to our library. we no longer have to write this part. So the struct that we wrote is the schema. You don't have to do this anymore in C++26. And that was the real win. And we also got to delete this. Everybody at some point had this in their code base. It's a bunch of macros. You use this to generate all of the metadata code that needs to be generated. It's really ugly. It took a while to implement, a lot of, at that time, Stack Overflow reading of how macro magic works. But we were able to delete all of it finally, because with reflection, you don't need it. Yeah. And we deleted that. We deleted our custom stuff to check that it has metadata, to list all the fields. We deleted every intro-gen metadata macro. And we deleted our third-party dependency, and this was this CTTI library that allowed us to manipulate this pretty function into usable names. So I show you this, and I show you how it works in my code base and in my pet project online that you can see. But what does this mean for you? So first thing, C++26 reflections have been voted in. Like the syntax, everything that I showed you, that is final. We know how that looks like. You can compile it. GCC shipped a compilable version of this. There's freflections, C++26, and freflection to enable it. There is a Clang fork for you Clang fanboys. There's a Clang fork. In my project, you will see this Clang fork used through Bazel, so people are using Bazel. And the Bazel repo basically clones the fork for you, compiles the compiler, and then uses this compiler to compile the project. And that is why we like Bazel. And the library adoption is getting there slowly, but it will be there. The good thing is that now that we know how C++26 reflection looks like, this is the perfect time to adopt the macro magic code if you haven't so far. Why? Because you know that it's going to go away. So when we did it in 2020, and then I showed this in 2022, people were like, okay, why would I introduce this to my project? Looks kind of dangerous, looks kind of off. How will it affect compile time? None of that matters, right? Because when C++26 reflection comes, you're going to start using it. So it's really nice to get your code base prepared to be aware of reflection. And you can implement this reflection using the macro approach even now in your code base. And when C++26 compiler comes into your shop, you can just delete all of these things, but your business logic will stay the same. So what I suggest is go take a look at this approach, how it's being used, introduce it, and now you know that it matches well with what is going to be shipped and what the language is going to support. If you want to get introduced with all of these concepts more, you'll have the QR code for my repo. You can read the proposals themselves. I don't think anybody would do that, but you can watch these talks by Barry. They're really good. They even show the first one here is fresh, and it shows you how reflection is used in other languages, and then it gets compared to what standard guys are working on next. So you can even get more inspired and add more macro magic to match what's going to come in new versions. You can check out the play around with reflections in Compiler Explorer. That's the easiest way to do it. And the best thing is just to go and build stuff.
It was Dusan Jovanovic. Dusan, thank you much for your speech. I think it was very interesting slides, and it's time to ask us some questions. I am sure there will be a lot of questions.
But before questions, let me remind you that we have interpretation feature because next talk is in Russian language. So if you need translation, you might want to take a headset on the reception.
Yes, question from me here. Thank you for the great presentation. But the question is, what does the standard have to say about reflecting against the standard types, like std vector you had in your example, aggregate type, which had vector as a member. So how comfortable should you be against reflecting against the standard types?
Really comfortable. Yeah, you just get back the meta info, and then you can ask things using those queries.
So it is allowed, and you can inspect against the private types. They don't define that as undefined behavior.
No.
Okay, thanks.
1, 2, 3. The question is about a fairy tale. Imagine a world with all our dreams came true. Are there some facilities to inspect the code, not the data types in C++? For example, access to type-checked AST or ability to change it. Is it something that is being discussed at committee? Do you have any opinion on would it be useful?
Thank you. It will be useful. And it will come. It's not what was shipped with C++ 26, but it's being discussed. I think the Barry's talk that I mentioned, you can go and take a look at what the standard guys are cooking next.
Thank
you. Just to repeat, can you modify the private fields of classes? No, you cannot modify anything with this. You can inspect stuff, and you can generate new code. That's it. No code modification was added, and this was a deliberate decision. Will it be added in new standards? Remains to be seen.
More questions? Okay, we have one more on the left.
Very quick, not maybe less of a question about reflecting on standard types. Be aware there's some problem with aliasing. You can't really easily reflect on alias types, and there are some problems. And I believe GCC aliases a lot of its standard types, so it's not really standard thing, I would say.
Okay, thanks. Any other questions?
Yeah, we have a question there.
Let me remind that you can ask questions in English, Russian, and Serbian language. So feel free to use any language. Also use C++ to ask a question as well as your favorite language.
Okay, thank you for your topic. Can you tell what is overhead for that feature?
Overhead is...
Did you compare or?
Yeah, so overhead is acceptable. Like... In standard C++ design philosophy, if you're not using it, you can enable the compiler flag and it will be zero overhead, right? If you're not using it. If you are using it, it will have some overhead. But for me, it's acceptable. But because it's such a powerful feature and transforms the way you write code, compilers will eventually speed up the implementation. It will get faster and faster. It will add less overhead on the compiler itself. But for me, the more important thing is the code that you're able to write, and for me, the overhead is totally acceptable, and you should embrace it.
How is your head when it goes over your head with the scripted code?
It's manageable, I think.
Okay, I have one question.
Yeah.
If we have no overhead, but we should pay something, maybe we'll pay by compilation time.
Yeah, of course. But you only pay for compilation time when you're using it, right? If you're not using it, you're not paying for it.
Yeah, and will the cost will be high?
It depends on you, right?
Gosh, I forgot we have PGO. We built it 4 times. Who cares about compilation time? Ask Alex.
So you want me to optimize computer and after then to compile my program with optimized computer. That's a great idea. Thank you.
Or even after you enable all of that reflection, you run the compiler with the PGO and optimize it to better optimize your code.
And get a very tiny Pomodoro app.
Okay.
Okay, some more questions? Можно по-русски, напоминаю.
Сербски також можемо.
Что ж, я думаю, что...
Don't be shy.
Да.
Okay, no questions, but we have QR code. Oh, one more question. QR code makes sense. It's a powerful
Another
thing.
question, can we reflect against the templates itself and get the template arguments and their concepts and constraints?
Concepts, nice. I don't think so. But when you reflect against the template, it gets reflected once it is rendered. So you're not aware that in syntax you reflect against the template type argument, but you're getting the reflection of the actual type that you're reflecting on.
Dear friends, your feedback is extremely valuable for speakers. Please use your phones. It's not scam. It's not. It's not about bitcoins and crypto. Trust me.
Thank you for your talk. I want to hear your opinion. What are the chances that this will be implemented in all major compilers in a usable form by the end of this decade, at least?
Oh, by the end of this decade for sure, because GCC implemented it, and it would the only lack is the standard library part, which is going to be, by the end of next year for sure. For Clang, I think the staffing there is low, so there is a working branch, but when that branch is going to be merged into Trunk, I think 27, 28 is a good timeline to expect this.
More questions? Okay, thank you so much, Dushan, for your talk. It was awesome.
Еще раз благодарю Душина. Действительно был потрясающий доклад. Следующий доклад будет на русском языке. Его прочитает Константин Облаков, инженер Яндекса. И доклад называется SIGSEGV Driven Profiler. У нас в C++ много чего драйвера. А здесь SIGSEGV Driven Profiling.
That's really interesting because usually SIGSEGV means I need GDB and not profiling. So Konstantin, take this in. Talk a lot.
Константин, давай проверим кликер. Сперва его нужно найти и убедиться, что он переключает слайды. Супер. Тебе слово.
используется как адрес внутри. Что, опять не работает? Ах, какая жалость. Последние биты у нас остаются на то, чтобы вычислить смещение байта внутри самой странички. В случае x8664 традиционно странички размером в 4 килобайта, и так как у нас все странички 4 килобайта, то даже сами таблички страниц, они тоже по 4 килобайта, и так как указатель у нас 8 байт, то получается 512 элементов каждый, то есть по 9 битов на каждом уровне. Традиционно там 4 уровня. Вот. Можно заметить, что, вообще говоря, обращение в память получается довольно-таки медленной операцией, сложной. У нас получается много-много-много всяких обращений в память ради одного преобразования. Поэтому на процессорах для этого используется специальная отдельная компонента, которая называется Memory Management Unit, которая упрощает это преобразование. И тем не менее, даже такое упрощенное преобразование все равно медленное, и поэтому оно еще и кэшируется дополнительно. И поэтому существует Translation Look-Aside Buffer, который берет и хранит, соответственно, последние адреса, которые мы преобразовывали. Кроме того, каждая страничка, как файл на диске, имеет свои собственные права. Ее можно читать, ее можно писать, ее можно запускать. Кроме того, у нас имеются всякие биты, связанные с тем, что трогали страничку, не трогали страничку, и в зависимости от этого операционная система может понимать, что страничка использовалась, не использовалась процессом. Размер конкретной физической странички, он архитектурно зависимый. То есть традиционно он на x8664 это 4 килобайта, а вот на моем MacBook это было 16 килобайт. Ну, вот так сложилось. Мы посмотрели только на сторону железа, а есть еще операционная система. И операционная система максимально ленивая. Она ничего не будет делать, если ее специально отдельно не пнуть. Если мы хотим выделить большой буфер на 1 гигабайт, то, скорее всего, никакой физической памяти выделено не будет. Операционная система просто пометит, что да, вот здесь мы обещали процессу память. Потом как-нибудь потом выделим. Если нам нужно форкнуть процесс, зачем всю память процесса копировать? Мы просто откопируем таблицу страниц. Ну и пометим какие-то из них как copy on write. Если у нас файл, он замапирован, то мы его не читаем. Зачем? Мы просто откладываем эту операцию потом, когда наконец-таки произойдет обращение к соответствующей страничке. Казалось бы, очень странная такая стратегия, но если посмотреть на тот же браузер, то в браузере есть рендерные процессы, и у рендерных процессов порядка 9 гигабайт виртуальной памяти замапировано, но из них используется только 200 мегабайт в физических страничках. То есть вся эта ленивая оптимизация приводит к тому, что ваши программы требуют меньше ресурсов. То есть операционная система экономит ресурсы. Из этого проистекают достаточно понятные следствия для разработчиков. Если вы делаете какие-нибудь базы данных, и вам важна скорость отклика вашей базы данных, вам нужно прогревать память. Вы должны обратиться к каждой страничке и убедиться, что она действительно появилась в физической памяти. Если вы салоцировали какой-то буфер, нужно обратиться к каждой страничке, чтобы она действительно появилась. После того, как эта память появилась, она может быть выброшена операционной системой обратно на диск или в файл подкачки. В этом случае вам нужно лочить эту память, обращаться к операционной системе и говорить, что не выгружай, это очень нужные для меня странички. Кроме того, вы можете говорить операционной системе различные подсказки о том, как использовать вашу память. Вы можете сказать, что она должна быть читаться последовательно, она должна читаться случайно. Вы можете вообще сказать, что она прямо сейчас мне не нужна, если что, выгружай. Кроме того, есть такая замечательная оптимизация, как пропускать часть уровней. Если у нас какие-то большие регионы памяти, которые отображаются в один непрерывный регион физической памяти, то мы можем пропустить часть уровней. Таким образом, существуют large и huge pages, которые, соответственно, 2 или 1 гигабайт на x8664, и они просто пропускают часть уровней. И за счет этого и преобразование становится быстрее, и вы реже получаете TLB-миссы. Что же у нас происходит на стороне операционной системы? Когда у нас ЦПУ попытался преобразовать виртуальный адрес в физический, он пробежался по TLB, он получил, что там нету ничего. Он пробежался по таблице страниц, не нашел ничего. После этого он генерирует прерывание page fault, которое обрабатывается ядром. И ядро старается в этом случае максимально быстро восстановить работу. Если это память обещана, но мы ее еще не выделили, давайте выделим. Если это файл, мы его не прочитали, давайте прочитаем и так далее. Можем откопировать на copy on write и прочее. В случае же, если операционная система не знает, что делать, она генерирует сигнал. SIGSEGV или SIGBUS. Конкретный тип сигнала зависит от ситуации, из-за которой вызвана, и от конкретной операционной системы. Например, если у вас проблема с правами доступа, то есть вы попытались записать в страничку, у которой права только на чтение, то Linux, скорее всего, вам сгенерирует SIGSEGV, а macOS, вот в моем случае, генерировал SIGBUS. Если у вас нет никакого обработчика сигнала, он не зарегистрирован, то тогда по умолчанию операционная система убивает ваш процесс и, возможно, если соответствующим образом сконфигурировано, делает корку. При этом вы можете зарегистрировать собственный обработчик на этот сигнал, и в этом случае будет передано управление в user-мод, вы будете сами обрабатывать эту ситуацию на своей стороне. В принципе, большинство ситуаций так или иначе разрешимы на стороне хендлера. В некоторых случаях вы можете восстановить права, если вы вдруг по ошибке их проставили не так. Вы можете замапировать новую страничку на соответствующий адрес. В некоторых случаях даже, это архитектурно зависимые трюки, можно скипнуть инструкцию, которая вызвала проблему, если вы понимаете, что это действительно так. Чаще всего просто программу крэшат с какими-то дополнительными дебаг-трюками, которые позволяют записать информацию какую-то. Но если вы реально проблему разрешили и вернули управление в операционную систему, то процесс продолжит нормально выполняться. И здесь есть очень важный слайд. Если вы запомните из моей презентации всего лишь один слайд, я хочу, чтобы это был вот этот слайд. Вы должны понимать, что каждый раз, когда вы проваливаетесь на следующий уровень абстракции, это приводит к замедлению работы с памятью в 10 раз. Буквально в 10 раз. То есть у вас общение между регистрами — это меньше наносекунд. Если вы обращаетесь в CPU кэш, это уже медленнее. Если обращение к реальной памяти еще медленнее, у вас происходит LB-miss, минорный page fault. Page fault отличаются. Минорный — это тот, который можно разрешить не обращаясь к диску, а мажорный page fault — это когда нужно обращаться к диску. И когда вам нужно обращаться к диску, то это тем медленнее, чем медленнее у вас диск. Поэтому самое худшее, что может произойти, это мажорный page fault. Поэтому прогревание памяти очень важно для баз данных, чтобы не напарываться на такие огромные задержки. Отлично. У нас есть segmentation fault, у нас можно установить для него обработчик. Зачем вообще нам нужно устанавливать обработчик? Во-первых, мы хотим понять, что же вообще произошло. Во-вторых, мы можем попытаться сделать какую-нибудь дополнительную работу. Например, всякие компиляторы типа GCC и Clang, они обычно в этом случае шлют сообщение на консоль: расскажите нам, как вам удалось написать такой код, что уронил наш компилятор в корку. Мне удавалось уронить и GCC, и Clang, это не очень сложная задача. Вот. Обычно где-то за полгода они фиксят этот баг. Если вы к ним обращаетесь, действительно заставляете соответствующий issue в трекере. Вот. Иногда это требуется для различных трюков с отладкой, которые я покажу чуть позже. Бывают вообще забавные фреймворки, например, Java Virtual Machine, она использует под капотом segmentation fault для генерации null pointer, эксепшенов, остановки тредов и многих других операций. То есть когда к вам приходит джавист и говорит, что вот, C++ плохой, там есть segmentation fault, а вот в нашей-то Java нет, они вам врут. Она у них есть, просто под капотом. Собственно, как зарегистрировать обработчик сигнала? Вам нужно создать функцию. Конкретно аргументы этой функции зависят от того, какие флаги вы передали в функцию SIGAction. И после этого вы регистрируете ваш обработчик через функцию SIGAction. В данном случае я зарегистрировал SIGSEGV обработчик. И я попросил с помощью флагов, чтобы мне дополнительную информацию о том, какая причина была, в SIG-инфоструктуре передали. Главные сложности при написании обработчика сигнала следующее. Вы не можете ничего аллоцировать. Потенциально происходит следующая ситуация. У вас имеется какой-то тред, который, возможно, прямо сейчас находился внутри аллокатора, может быть, внутри какого-то лока или еще чего-нибудь. И прямо поверх него сейчас вызывается обработчик вашего сигнала. В результате, если вы ждете, пока этот лок будет отпущен, он никогда не будет отпущен, потому что вы находитесь ровно поверх того самого треда, который его занял. Это означает, что если вы попытаетесь сделать это с каким-нибудь аллокацией, то аллокация потенциально вызывает какие-то локи внутри аллокатора, и вы сталкиваетесь сами с собой, этот процесс никогда не закончится. У вас ограниченный набор системных вызовов, которые помечены как доступные в случае обработчика сигналов. Вы не можете использовать локи, у вас ровно так же ограниченное использование атомиков, потому что если вы попытаетесь с помощью атомиков взять какой-нибудь спинлог, у вас те же самые проблемы. Потенциально вы в том же треде, который этот спинлог занял. Из-за того, что вы не можете аллоцировать, у вас на самом деле сильное ограничение на использование сторонних библиотек, потому что большинство сторонних библиотек где-то внутри себя делают аллокации. Например, этим занимается std stack trace. То есть вы не можете их использовать. И из-за того, что вы не можете аллоцировать, вам совершенно по-другому нужно смотреть на свой код. Потому что у вас нет возможности сделать ни new, ни malloc. У вас должна быть какая-то совершенно альтернативная стратегия разработки кода. Главная сложность – вы не можете ничего аллоцировать. Что же нам делать с этим? А делать на самом деле получается достаточно просто. У нас есть возможность заранее аллоцировать. Мы знаем, какие структуры нам потребуются внутри нашего обработчика сигналов. Мы можем заранее все это аллоцировать. Мы можем использовать память на стеке. Память на стеке аллоцируется за счет более простых низкоуровневых механизмов смещения стек-поинтера на процессоре. Поэтому она доступна. Если вы ловкие, смелые, умелые, вы можете попытаться придумать лог-фри, неаллоцирующий, модифицирующий алгоритм, который будет нормально работать в случае обработчика сигналов. Но нужно быть аккуратным и аккуратно все это реализовывать. Несмотря на то, что у вас ограниченный набор системных вызовов, неожиданно среди них есть write. То есть можно писать файл спокойно, прямо из обработчика сигналов, записав какую-нибудь дополнительную информацию. Например, вы можете на ту же самую консоль выписать сообщение для пользователя. Формально backtrace из POSIX — это implementation defined, можно ли его использовать внутри обработчика сигналов, но очень многие реализации обработчиков сигналов закладываются на то, что его можно использовать. Например, в Chromium base debug collect stack trace, в частности, полагается на backtrace из POSIX для очень многих архитектур. Соберем из этого очень странный профайлер. Очень безумный план. Давайте зарегистрируем свой собственный обработчик сигнала, просканируем всю виртуальную память процесса и пометим все странички как недоступны ни на чтение, ни на запись, ни на выполнение. Естественно, бизнес-логика продолжит выполняться и будет сталкиваться со страничками, которые мы запретили. После этого мы прямо в обработчике сигналов восстанавливаем права, которые были до этого, и собираем стек, который это вызвал. Без символов. Символизация требует аллокации. А символизировать мы это будем в сканирующем треде, в отдельном, и дампить файл. После этого у нас код неожиданно работает приблизительно с той же самой скоростью, за исключением маленьких иканий на вот этих ловушках. И попытаемся из этого получить какой-нибудь очень полезный профит. Это совершенно другой тип профайлера, чем те, которые вы видели до этого. Он не пытается оптимизировать количество ЦПУ, которое вы тратите. Он не пытается отследить, какие у вас задержки на локах или IO. Он не пытается отследить, кто аллоцирует память. Потенциально вы аллоцировали гигабайтный буфер, но если вы ни разу его не трогали, он никак вообще не влияет на потребление памяти вашего процесса. Это, конечно, можно было бы исправить, но тем не менее это никак не влияет. Это означает, что на самом деле самое важное для потребления памяти вашим процессом, кто трогает память. И используется ли она до сих пор. Для этого вы можете собирать стеки раз в определенное время и смотреть, какие странички до сих пор используются, а какие перестали использоваться. И если они сейчас не используются, может быть, их можно освободить. Шикарная идея, осталось реализовать. Нам потребуется какое-то количество информации, кода, и я здесь не буду сильно останавливаться на коде, потому что он довольно-таки замудренный, и там потребуется много всяких трюков. Я пробегусь по нему по верхам. В любом случае нам потребуется по каждой виртуальной страничке иметь какую-то физическую информацию, то есть нам потребуется то же самое префиксное дерево, что мы используем для таблиц страниц. Реализуем его по-своему на C++. Нам потребуется запись, куда мы будем складывать стеки. Заранее мы аллоцируем на 60. 60 слишком мало на самом деле для блинка. Для блинка желательно там 180 или 200, но просто как пример реализации. Потребуется некоторые переменные, сколько в этом стеке фреймов мы сохранили, текущее поколение стеков, которые мы собираем, и права, с которыми была эта страничка до того, как мы расставили ловушку. Нам потребуется арена, где мы будем соответствующие структурки складывать. Нам потребуется свой собственный карманный аллокатор, который мы будем использовать в сканирующем треде, чтобы не сталкиваться с основным аллокатором и чтобы точно знать, где наши структурки лежат в памяти. Это очень простой наколеночный аллокатор, он даже без выравнивания и всяких многих других трюков. Я здесь обращаю внимание только на вторую строчку. Это in place new. практически большинство разработчиков никогда это не видели в своем коде и вряд ли когда-либо увидят, потому что это нужно только создателям аллокаторов и тем, кто реализует какой-нибудь std-вектор или еще что-нибудь подобное на низком уровне. Это вызов конструктора по конкретному адресу без реального выделения памяти. Нам потребуется немножко log-free логики. В данном случае это инициализируемый один раз указатель. И вот мы собрали наш простецкий аллокатор. Только для сканирующего треда. Никто другой больше им пользоваться не будет. Нам потребуются ноды этого префиксного дерева. Я не буду здесь сильно останавливаться. Немножко магии с битами. Вектор, вернее, массив с полями, с указателями на более нижнем уровне. Нам потребуется метод find для читающих тредов. Нам потребуется find.oalloc для пишущих тредов. И нам потребуется pattern visitor, чтобы пробежаться по всем стекам, собрать их, просканировать и записать куда-нибудь в файл. Ну или обновить соответствующую информацию. Ну и надо в шаблонную матрешку заканчивать каким-нибудь классом. Мы будем заканчивать final node, который будет хранить, собственно, нашу структуру и который будет отдавать наружу через соответствующие методы. Вот. И таким образом собираем дерево. Реализацию оператора квадратной скобки, find и visit оставляю читателям на, так сказать, в качестве дополнительного упражнения. Не очень сложно. Собственно, собираем из этого профайлер. Как собрать профайлер? Нам нужно выровнять адрес, который у нас есть в памяти, до адреса странички. Нам нужно вызвать mprotect с соответствующими правами и размером. И вот получается наш профайлер. Берем арену, выделяем там информацию по страничкам, передаем в конструктор профайлера указатель на него глобальный, чуть позже я объясню зачем, и метод процесс, который позволяет нам обработать адрес. Собственно, нам потребуется где-нибудь глобальный указатель на наш профайлер, и в нашем segmentation fault handler мы будем проверять, что этот профайлер существует, и если он существует, то отправляем в него информацию. Из этого sig-info достаем только c-adder, больше нам ничего не нужно. Где-то создаем этот профайлер, и туда обязательно нужно передать указатель на переменную global профайлер, чтобы случайно не поставить на нее ловушку, потому что в этом случае наш segmentation fault handler перестанет нормально работать. Собственно, как обрабатываем адрес, выравниваем адрес до адреса странички, проверяем, есть ли у нас информация. Если у нас есть информация, восстанавливаем права. Сначала восстанавливаем права на страничку, потом собираем стеки. Только именно в таком порядке. Мы не можем собирать стеки раньше, чем восстановим права, потому что потенциально мы сами на себе задедлочимся. И нам нужно собрать стек. Здесь очень простой log-free паттерн. Кто первым пришел, тот и записал стек. Если уже стек записан, мы проверяем, если наше поколение оказалось более поздним, то мы заменяем стек, который там был. Если одновременно с кем-то столкнулись, ну, пробуем и вываливаемся. Осталось просканировать память. Сканирование памяти сильно архитектурозависимая штука, поэтому останавливаться на этом сильно глубоко не будем. Но вот примерно такую реализацию ЖПТ предложила мне реализовать. Ну, в общем, похоже на правду. Тут главное — это Mac VM Region Recurse, который, собственно, пробегается по всем виртуальным регионам памяти. И дальше мы по каждому региону делаем какую-то операцию. Мне нужно только те регионы, куда можно читать, писать. Я не хочу трогать регионы памяти, где есть какой-то запускаемый код. Я хочу только приватные регионы, которые принадлежат этому процессу и не шарятся ни с каким другим. И я исключаю несколько дополнительных регионов, а именно я не хочу трогать стеки и всякие другую метаинформацию, которая потенциально мне повредит. Собственно, для каждого региона я пробегаюсь по всем страничкам, проверяю, если я ее не должен защитить, то есть она не содержит, собственно, мои структуры и не содержит указатель глобальный на мой профайлер, то я вот такие структурки я пропускаю, а все остальные, на них я расставляю ловушки. Я здесь не упоминаю, но вообще говоря, это важно для реализации, что регионы памяти между сканированием могут поменяться. И потенциально у нас регион был замапирован, перестал быть мапирован. И в этом случае нам нужно каким-то образом это отслеживать. Я это не стал здесь упоминать, потому что это удваивает листинг кода. Нужна отдельная система передачи информации про защиту регионов памяти. Я чуть позже объясню, зачем это. И я здесь никак не рассказываю, как мы символизируем стеки, собираемые из POSIX. Это отдельный код. И потребуются маленькие небольшие паузы между сканированиями, иначе процесс станет слишком неотзывчивым. Он будет постоянно сталкиваться только-только и делать с ловушками. Поэтому небольшую паузу, там 5 секунд, и, пожалуйста, можно бежать в следующее сканирование. Темная сторона этого решения. Почему это не так просто? Все это замечательно, красиво работает, когда мы трогаем память в юзерспейсе. В этот момент все замечательно, отлично работает. Но в тот момент, когда эта же самая память требуется какому-то сисколу, сискол вместо того, чтобы вызвать наш обработчик сигнала, вместо этого возвращает invalid access и идите подальше. Все, ничего не работает. Это означает, что перед каждым сисколом нужно вставить отдельный гвард, который говорит, вот эту память, если там есть ловушки, снимай, а если сейчас пытаешься сканировать, ни в коем случае не ставь там ловушки. Вот эту информацию нужно докинуть, там непростой код, но он тоже удваивает, собственно, листинг, небольшой log-free паттерн, и все работает. Собственно, мне в случае macOS потребовалось защититься от Kevin64, MacMessage, read, посред mutex и посред cont. Можно заметить, что это совершенно неполный набор сигналов. Здесь, например, нету сигнала write. Почему? Да потому что сигнал write, прежде чем вызвать на соответствующем буфере, мы этот буфер сами трогали. А если мы его трогали, то потенциально мы все ловушки уже сняли. И поэтому на самом деле, конечно же, по-хорошему здесь тоже нужно гвард. Но в реальности обычно это не требуется. Я, в принципе, готов к тому, что в 10% случаев эта штука bleeding edge будет падать с какими-нибудь странными ошибками. 10% ошибок — это не страшно. На самом деле она падала реже после того, как я расставил большинство этих ловушек. И небольшая демка, как это работает. Заходим в Яндекс-браузере на сайт конференции. Заходим на сайт конференции для Москвы, заходим на сайт конференции для Белграда, все загрузилось, все работает. В этот момент стеки собираются. И у меня имеется вот task manager браузера, я смотрю, какой у меня пит у процесса, чтобы по нему запустить мой shell скрипт, который собирает соответствующие стеки и делает из них флейм-графы. Вот он сейчас в первом шаге, пока что ничего не нашлось, потому что не прошел даже первый цикл. Тем не менее, мы можем посмотреть, вернуться на эту страничку, она продолжает спокойно, нормально работать. То есть там стеки вот собираются, вот мы можем посмотреть в фоне, что это происходит. Все нормально работает, она скроллится, она работает. Тот же самый процесс, ничего страшного. В этот момент скрипт работает, скрипт собирает стеки. Я тут отдельно убеждаюсь, что пит ровно тот же самый, чтобы не ошибиться, не перепутать. В этот момент я уже могу смотреть, что файлы флейм-графов еще пока не созданы. Я создаю их только с третьего шага, потому что я хочу их делить на свежие и старые. А чтобы свежие и старые, я делю там, грубо говоря, 2 последних поколения — это свежие стеки, все остальные старые. Вот у меня 3 шага отработало, и у меня, пожалуйста, построились флейм-графы. Я могу посмотреть прямо сейчас, что происходит в памяти процесса. Каждый стек здесь — это 16 килобайт, страничка. В результате, чем шире, тем больше эта часть кода трогает памяти. Более того, эта штука одновременно обновляется. То есть процесс продолжает жить, с ним ничего страшного не произошло. Я могу делать рефреш на страничке и посмотреть, что происходит в фоне с процессом. Стеки смещаются, где-то что-то появляется, где-то что-то исчезает. Давайте попытаемся соптимизировать память браузера. Вообще, почему браузеры едят так много памяти? Наверное, потому что разработчики жадные. Конечно же, нет. Основная проблема — это то, что пользователи открывают все больше и больше вкладок. Буквально есть статистика, что где-то приблизительно за последние 5 лет пользователи открыли приблизительно в 2 раза больше вкладок, чем в предыдущие годы. То есть это получается, что каждое следующее поколение пользователей считает, что 100 табов — это уже нормально, давайте 200. У нас есть статистика, что есть какой-то пользователь с 7000 вкладок. Как он живет, не очень понятно. Мы не знаем, кто это, потому что данные анонимизированы, но тем не менее такие пользователи существуют. И мы пытаемся как-то улучшить жизнь этих пользователей. При этом разработчики сайтов продолжают вставлять все больше картинок, все больше JavaScript. Есть ощущение, что у них есть такая кнопочка «Включить весь JavaScript в мире в мою страничку». При этом новые стандарты, они продолжают совершенствоваться, и каждый новый стандарт говорит, что давайте хранить еще дополнительную информацию. И разработчики браузера, окей, мы храним еще информацию по этой страничке. В результате получается, что все это растет, все это экспоненциально растет, а кроме этого существует еще такая важная причина, как безопасность. У вас в какой-то вкладке хранятся банковские данные, ваши приватные данные. И есть другая вкладка, в которой какой-то хакер написал свой JavaScript и пытается эти данные утащить. У него не должно быть никакой возможности это сделать. Это означает, что каждый рендерный процесс находится в песочнице. И эта песочница требует ресурсов, она требует памяти. Что мы можем здесь, вот чем мы можем здесь попытаться пожертвовать? Ну, в первую очередь, кажется, пользователь завел слишком много вкладок. Ну, наверное. Значит, надо попытаться подумать, что мы можем сделать с этими фоновыми вкладками. Ну, конечно, можно было бы их всех убить, но, наверное, это, неправильная логика. Давайте попробуем посмотреть, чем вообще с ними происходит. Посмотрим на них с помощью нашего профайлера. Если посмотреть с помощью профайлера, можно посмотреть, на что в основном тратится память у фоновых вкладок. И там получается довольно-таки забавная ситуация. Каждая вкладка фоновая, после того, как с нее ушел пользователь, она пытается максимально себя сжать, чтобы как можно меньше занимать памяти, чтобы у пользователя осталось как можно больше памяти. Там запускается garbage collector, причем не такой, как на активной вкладке, там, с маленькими паузами, а он запускается полностью нелимитированный на всем регионе памяти. Очищаются все возможные кэши. Если имеются JavaScript-строчки длинные, то они сжимаются зипом, возможно, даже сбрасываются на диск. Причем основная память рендерного процесса — это как раз в основном JavaScript-строчки. Какие у нас есть стратегии помочь процессу? Ну, понятное дело, что мы можем с помощью garbage коллектора все структуры, которые есть в памяти процесса, как-то промаркировать, понять, какие кому нужны, какие не нужны, и какие-то лишние собрать. Это хорошо, замечательно работает, если вы все библиотеки смогли накрыть. А у вас очень много библиотек. И кто-то эти библиотеки пишет, вообще не зная про то, что у вас существует garbage коллектор, и им начхать на то, что существует ваш garbage коллектор. Они аллоцируют какие-то буферы внутри себя в этих библиотеках. Они аллоцируют какие-то дополнительные структуры, которые не собирают и никак вообще вам не репортят. И в результате возникает проблема, что garbage коллектор не все накрывает. Кроме того, есть операционная система. А вот у операционной системы есть информация о всех ваших страничках. Она знает каждую страничку лично, когда она ее выделяла, зачем она ее выделяла, какому процессу. В результате можно ее попросить сдампить лишние странички на диск. Но тут возникает проблема. Если посмотреть на вот этот вот путь, garbage коллектор трогает все странички. Вы оставили страничку в фоне, но garbage коллектор продолжает по ней бегать итеративно. Он не нашел мусора, не нашел мусора, не нашел мусора, но он продолжает трогать все странички. С точки зрения операционной системы эти все странички активные. Их всех кто-то трогает. Плюс там минимально что-то делает JavaScript с какими-то своими хендлерами, но в основном это garbage коллектор, который бегает. Это означает, что с точки зрения операционной системы все странички грязные, значит, их нельзя оптимизировать, и таким образом garbage коллектор говорит операционной системе, ты ничего не можешь делать. То есть оптимизация памяти мешает оптимизации памяти. Как должен выглядеть тогда хороший таб с точки зрения такой логики? Ну, окей, мы очистили все кэши, сжали все строчки, запустили garbage коллектор, остановили JavaScript, остановили garbage коллектор, попросили операционную систему сбросить большинство памяти, ну, просто забрать ее. Может быть, она ее оставит в память, может быть, сбросить на диск. Это ее личное предпочтение в зависимости от того, какая сейчас нагрузка в системе. И если мы посмотрим в этот момент на Windows Task Manager, он говорит, что ваш таб вместо 200 мегабайт занимает 5-15. Совсем другое дело. А если пользователь вернется, то операционная система мгновенно возвращает эти странички обратно. Это сильно быстрее, чем перезагружать это все по сети. Результаты приблизительно такие. Это оптимизирует 20% памяти браузера. Это довольно-таки специфическая цифра. Надо понимать, что это оптимизация на определенной квантиле пользователей, потому что пользователи с одной вкладкой здесь, наверное, не очень разумно смотреть. Разумно смотреть те, у кого действительно много вкладок. То есть это определенный перцентиль пользователей, и для них мы смотрим статистически достоверное улучшение. Это означает, что у конкретного пользователя это может давать как сильно больше, так и сильно меньше. Зависит от случая. И вот недавно было исследование компании IA Telecom Daily, и по их исследованию мы неожиданно вышли в топ-1 по оптимизации памяти на Windows. Это шикарный, замечательный результат, но надо понимать, что это вот конкретные кейсы, и понятное дело, что вы всегда можете найти конкретный кейс, где какой-то конкретный браузер, если знаете его потроха, вы всегда можете найти конкретный кейс, когда один браузер обгоняет другой. Другое дело, что каждый раз эти кейсы будут становиться все сложнее, сложнее, сложнее. И это означает, что в принципе, если существуют какие-то компании, которые снаружи измеряют производительность и не обнаружили, что вы лучше, то это означает, что, ну, по крайней мере, вы движетесь в правильном направлении. Всем спасибо.
Константин, спасибо большое. Было очень интересно. Впечатляющий результат про номер 1 экономии по памяти. Я считаю, это заслуживает дополнительных аплодисментов. Вот. А сейчас есть время, собственно, задать вопросы. It's time to ask questions. Okay.
Здравствуйте, спасибо за доклад. Хотел бы понять подробнее, что вот эта вот карта в СВГ помогает обнаружить. То есть она помогла обнаружить работу garbage коллектора?
Да, она позволяет, во-первых, обнаружить работу garbage коллектора, во-вторых, она позволяет понять, в каких функциях и в какие моменты вызываются какие операции. И за счет этого мы можем понять, в какой момент и в каких функциях вставить соответствующие вызовы. То есть, грубо говоря, профайлер вам не нужен для того, чтобы реализовать ваше решение. Но без профайлера у вас не будет понимания того, что нужно делать. То есть если у вас вдруг снизошло озарение, что нужно делать именно так, вы можете это сделать без профайлера. Чтобы это озарение снизошло, без профайлера это тяжело. Собственно, профайлер позволил понять, что есть память, она вот так вот используется, и вот в этих местах у нас имеется такая сложность, которая приводит к тому, что если мы просто попросим операционную систему сделать свои трюки, чтобы она соптимизировала память, это не сработает. Почему? Потому что garbage коллектор вернет все эти странички назад. То есть мы понимаем, что нам нужно не просто обращаться к операционной системе, нам нужно взаимодействовать с другими подсистемами и в нужный момент сказать: теперь остановись, а теперь ты работай. И вот эти вещи, они позволяют, профайлер позволяет обнаружить. И благодаря ему это получается сделать максимально быстро и эффективно. Потому что, в принципе, все то же самое можно, наверное, прочитать в коде, понять, как он работает и разобраться. Но если это у тебя кодовая база размером с Chromium, ты это будешь читать всю свою оставшуюся жизнь.
Спасибо.
У меня такой вопрос. Правильно ли я понимаю, что это что-то типа софтверной реализации профайлера памяти из VTune? Или VTune привязывает стейки к скорости, а вы привязываете стейки к размеру?
Большинство профайлеров привязывает стеки к тикам процессора. То есть в тот момент, когда профайлер, это обычно называют профайлером бедного человека, когда ты берешь и собираешь в определенное количество тиков стек. В этом случае, так как стеки собираются раз в определенное количество тиков процессора, у вас автоматически фокус получается на наиболее горячих путях, где в основном тратится ЦПУ. А у меня стеки собираются в тот момент, когда страничка трогается. Поэтому у меня фокус на тех кусках кода, которые трогают странички. Поэтому фокус меняется. Из-за этого это получается другой профайлер. Можно было бы делать фокус на new или malloc, и тогда мы понимали бы, кто аллоцирует. Но так как меня не интересует, кто аллоцирует, а меня интересует потребление памяти, то я в первую очередь фокусируюсь на тех, кто трогает код, трогает память.
Ну просто в iTunes в том же там есть возможность именно ограничить инструкции, которые он будет считать. То есть сколько инструкций обращения к памяти произошло по данному стэк-трейсу.
Если вы читаете одну и ту же страничку подряд взахлеб в цикле, то, наверное, у вас будет очень большая статистика по чтению, но это будет всего одна страничка. А здесь фокус на том, что я пытаюсь понять общие паттерны использования памяти по страничкам в целом. Мне нужно понимать в целом, на что уходит память, потому что если вот у меня опять же есть этот гигабайтный буфер, и я где-то какие-то странички потрогал, то не то, что я аллоцировал буфер, виновато, а то, что я потрогал буфер, виновато в том, что память потребляется.
Так, вот там вот есть рука в самом конце. Еще.
Можно задать вопрос? Вопрос такой. Вот у вас было написано в презентации, что вы останавливаете JavaScript и останавливаете garbage collector. А потом вы его как-то включаете для фоновой вкладки? Или как это вообще работает? То есть, если я
есть много политик внутри Chromium, какие странички можно останавливать, какие странички нельзя останавливать, какие странички можно останавливать на время и так далее. Там, естественно, куча эвристик поверх этого наложена. Если у вас какая-нибудь страничка, которая требует нотификации пользователя, например, мессенджер, ее никто не будет никогда останавливать, ни в коем случае удалять, потому что это очень важно для пользователя. Пользователь может заметить соответствующие сайд-эффекты. Если там играется аудио, видео, ни в коем случае нельзя трогать, потому что это ровно так же аффектит пользователя. Тем не менее, большинство вкладок, которые пользователь завел, он завел один раз и убежал, он про них забыл. И вот эти вкладки, они в первую очередь являются главным источником мусора в памяти браузера. И в первую очередь на них должно быть сфокусированы все соответствующие оптимизации.
То есть выключение JavaScript и garbage collector, оно делается только для некоторых вкладок?
Да.
Окей, хорошо, спасибо.
И более того, это делается далеко не сразу, а в тот момент, когда мы понимаем, что пользователь, скорее всего, забыл про нее. То есть у нас есть некоторое понимание, и надо сказать, что пока я вот всю вот эту вот оптимизацию делал, я исследовал очень много вещей, связанных с забыванием человеком. Я исследовал краевой эффект, есть эффект контекстной памяти, есть дверной эффект. Все эти эффекты, на самом деле, они влияют на то, как пользователи используют браузер. То есть можно просто читать Википедию и смотреть по данным, и вы будете обнаруживать каждый из этих эффектов. Это просто чудесное пособие по психологии.
А можно я кратко дополню прежде всего вопрос? Если, например, разработчики решили сделать красиво и запустили снег на страничке, у меня идет снег, это значит, что она никогда не будет выгружена, правда же?
Со снегом у меня отдельные грустные воспоминания, потому что один разработчик ошибся в JavaScript, и в результате у него снег падал все больше и больше. И памяти эта складка плодила все больше и больше, и к нам прибегали пользователи с жалобой, почему у меня вкладка в 1 гигабайт. Это было из-за снега. Поэтому не надо делать снег, пожалуйста.
Костя так погрузился в оптимизацию памяти, что снег измеряет гигабайтами теперь. Костя, вот
я скорее багрепортами измеряю снег.
Я хочу напомнить, что у нас есть трансляция, и у тебя есть возможность обратиться к пользователю, у которого открыто 7000 вкладок. Что бы ты ему сказал?
Не надо так, друг.
Пожалуйста.
Ну, на самом деле есть два типа пользователей. Я их замечал на данных. Я могу сказать, что есть пользователи, которые забыли про кнопку «Закрыть вкладку». Это очень забавные пользователи. А есть пользователи, которые познали какое-то бесконечное DAO в мейнтейнинге своих вкладок, и они способны в 1000 вкладок ориентироваться. И когда я говорю ориентироваться, это буквально человек такой: так, я был на 1020 вкладке, сейчас я переключаюсь на 30-ю, а сейчас на 52-ю. Почему? Да я как-то сам не знаю. Я в шоке, как эти люди существуют, но существуют.
Мне немножко стыдно признаваться, я один из таких людей, у меня есть свой плагин, который позволяет переключаться.
Я тоже думал, что это плагин какой-то. Это какой-то плагин.
Вкладок.
Да. Спасибо за доклад. У меня такой вопрос. А рассматривали ли возможность использовать eBPF, чтобы собирать стэк-трейсы? И не знаю. Так бы можно было, наверное, в самом процессе ничего не менять и просто в ядре поставить.
В ядре, наверное, тоже интересно было бы поставить, но тут важный момент, что именно нужно ставить вот эти ловушки, и политику того, как расставлять ловушки, на каких страничках, она софтверная. Я вот специально отдельно написал, какие странички мне нужно выделить, какие я исключаю, почему я их исключаю, и куда я складываю стеки, и как я их собираю. И это все зависит от конкретного запуска. И надо понимать, что со стороны ядра часть некоторой информации уже утеряна, и ее очень сложно восстановить. В частности, там есть такая неприятная особенность, что в современных ядрах адрес, куда мапируются конкретные библиотеки, он рандомизируется для безопасности. И в результате, если вы соберете стэк без дополнительной информации о том, где лежали библиотеки, то это становится бесполезным. И вам потребуется очень много трюков со стороны операционной системы, чтобы воспроизвести то же самое. А это решение оказалось на самом деле не слишком большим патчем. Ну, то есть это больше, чем то, что я показал, раза в 3 или 4. И там библиотека либо диспатч съела мне весь мозг. Но, тем не менее, более-менее это реализуемо на коленке. Там, условно говоря, первая реализация у меня была сделана там, за 2 дня. Я просто взял, придумал идею, попросил GPT сделать. После этого я выкинул половину кода, переписал сам. Ну и, в общем, оно заработало. GPT отлично сделало вещи, которые архитектурно зависимы, типа сканирования, но в всяких лог-фри алгоритмах оно лажает, к сожалению, часто.
И можно тогда follow-up, насколько это распространяется на другие программы, сколько нужно
это легко заимплементить вручную в конкретном проекте, если большинство сисколов у вас так или иначе сосредоточено в какой-то конкретной базовой библиотеке. А в больших проектах обычно стараются все сисколы, а если это какая-то платформа независимый проект, то он старается все сисколы унести в какую-то отдельную маленькую библиотечку, чтобы они не расползались по всей кодовой базе. И тогда вам нужно в конкретных этих точках расставить соответствующие гварды, и все действительно делается легко. Но если это у вас какой-то такой очень наколеночный проект, где сисколы разбросаны по всему коду, то это становится тяжелее. Это не становится совершенно невозможным, но это тяжелее. В принципе, существуют отдельные флажки у компиляторов GCC и Clang, которые позволяют вам конкретные сисколы сделать для них свой кастомный раппер. И можно применить этот трюк, но это потребует полной пересборки всего кода с этими флажочками. Я не хотел полной пересборки кода, я пересобрал только конкретные CC-шники, в которых были соответствующие сисколы. И это работает. В результате, грубо говоря, 99% объектных файлов кода браузера остались теми же самыми.
Спасибо. Давайте вот сейчас Душин вопрос, а потом там еще вот вдалеке очень давно поднимается рука. Вот передайте сюда, пожалуйста.
Thank you. So, what about WebAssembly and not JavaScript? Does it interfere with your technique, and will it prevent a tab from being offloaded if WebAssembly code is being executed?
From point of view of the browser, mostly all of this WebAssembly and JavaScript are just some structures in C++ which are maintained. So it doesn't matter how they produced, it doesn't matter how they are processed by JavaScript or some other client code. It's just some calls to C++ code. So from point of view of C++ in browser, it's just some external calls which maintain this data. So it doesn't matter from this point of view.
Так, можно задать? Спасибо за доклад, очень интересная идея. Мой вопрос по поводу производительности. Вот у вас основа идеи заключается в том, что мы внедряемся в хендлер, вот, и как мы знаем, обработка сигналов — это очень тяжеловесная операция. И вот насколько эффективно и быстрее, чем другие профайлеры, получается ваше решение, или, может быть, наоборот, медленней?
Я хочу сказать так. На практике, вот я показывал демку, там вообще незаметно то, что процесс замедлился. Ну, то есть я скроллю ровно с той же самой скоростью, никаких проблем. Дело в том, что надо понимать, что за каждое сканирование всей памяти расставляется не большее количество ловушек, чем есть виртуальных страничек. И на них, соответственно, имеются соответствующие... Вот, когда на них код натыкается, то вот он натыкается за каждое поколение не больше, чем расставлено ловушек. В результате там получается по цифрам что-то порядка 5000 вызовов. 5000 вызовов, но это вообще ни о чем. Это никак на перформанс не влияет. В случае браузера это вообще ни о чем. Ну вот прям вообще ни о чем.
Да, понял. Спасибо.
Да, извините, я еще один раз задам вопрос. V8, кажется, знаменит тем, что он очень любит большие адресные пространства себе мапить, а потом не особо их использовать. По крайней мере, я себя очень замечал, когда локально просто смотрел на потребление виртуального адресного пространства браузером. Вот. там VS Code открыть или еще что-нибудь такое, постоянно видно, что очень много виртуальной памяти занимается. Вот, я не очень понимаю, по какой причине вот этот вот скан всей этой памяти не занимает невероятное количество времени. Что-то...
Дело в том, что мне нужно только пробежаться под этим регионом. Этих регионов на самом деле не очень много, их несколько сотен. Ну, то есть, грубо говоря, у меня здесь получается порядка сотни колов. Как я уже сказал, там получается порядка 9 гигабайт виртуального адресного пространства. Я не просто так с потолка эту цифру взял, а это вот как раз из моего профайлера выкатывается в качестве дополнительных всяких интересных фактов. И вот 9 гигабайт можно поделить на 16 килобайт, можно понять, сколько там будет вызовов на соответствующие структурки. И там, в принципе, я вот залоцировал 500 мегабайт под эти структурки. На самом деле там даже сотни не набегало. Я просто на всякий пожарный завожу побольше, чтобы в случае чего никаких проблем точно не возникало и решение работало более стабильно.
Круто, круто. Спасибо.
Спасибо за доклад. Вопрос такой, чуть более высокоуровневый. Вот ты говорил про вкладки, как их используют. У меня всегда вызывало недоумение, почему вообще эти вкладки люди хранят. То есть на моем личном опыте, когда я чищу браузерную историю своих бабушек и дедушек, там порядка 1800-900 вкладок может быть, но браузер сам мотивирует пользователей создавать новые вкладки. Они не умеют их закрывать. Они хотят что-то найти, и они пишут в новое сообщение в строке поиска и создают тем самым новую вкладку. Они никогда к ним не вернутся. Почему бы их не хранить в виде строк и перезагружать? Да, перезагружать долго, но типа трейд-офф.
В некотором смысле так и происходит. Дело в том, что когда вы закрываете браузер, полностью закрыли браузер, например, выключили компьютер, включили его заново, и заново открываете браузер, большинство вкладок не запущено, потому что их, в принципе, состояние невозможно сейчас сохранить. Это какой-то JavaScript, который где-то там в рантайме что-то делал. Поэтому эти вкладки, они перезагружаются с нуля. И по сути своей по ним хранится только вот эта вот информация про URL. Ну, там плюс-минус дополнительная информация про то, как вы ходили вперед-назад по истории. Вот эта информация может еще дополнительно храниться. И поэтому этой метаинформации действительно килобайты. Там есть некоторая сложность с тем, что хромиумный код, несмотря на то, что он очень хорошо мейнтейнится, и там очень много хороших политик, там иногда бывают различные баги и очень сложные баги. И мы недавно обнаруживали и много раз оптимизировали соответствующие куски на наших профайлах, когда обнаруживались квадратичные алгоритмы от количества вкладок. И в результате получается, что вот в Chromium оно так работает, нам нужно это выкинуть и переписать заново, потому что оно работает плохо. Очевидно, что Chrome, наверное, имеет какую-то свою реализацию, они не очень заботятся той, которая в Chromium, и поэтому баги остаются в коде и мешают. Но в общем и в целом, по идее, должно быть равносильно килобайту хранящейся информации о том, какие там были урлы. К сожалению, урлы бывают очень длинными. Бывают некоторые сайты, которые прямо в URL кодируют всю историю общения с пользователем, сотворения мира. Ну вот что поделать.
Спасибо большое, Константин. Я напоминаю, что совершенно обязательно и необходимо достать сейчас свой телефон, отсканировать вот этот замечательный QR-код и поставить оценку докладу. Кто не успел задать вопрос, для этого есть потрясающая возможность, потому что прямо сейчас будет небольшой перерыв, 30 минут. Подождите, еще не убегайте. Парочка объявлений. Евгений, переведи англоговорящим гостям.
So it's time for break. You might want to drink coffee, talk, make new friends, but only after you have scanned this QR code and rated our speaker. So we will continue at 3:50, and there are two tracks. One is for another excellent talk about Google Highway library for SIMD programming. And also we have a workshop about agentic coding, I guess in C++. So you might want to visit either one, but as I understand, some kind of pre-registration is required for that workshop. So take your time, enjoy the break. Rate the speaker, please.
Небольшое объявление. Во дворе все еще будут гонки на роверах. Кто не погонял роверы, пожалуйста, проходите туда. Это прикольно. Переведу, что дальше желающие, кто зарегистрировался на воркшоп, могут пройти на 3-й этаж. А тех, кто нет, мы ждем на очень классном докладе про SIMD. И да, вот мне сейчас сказали, что на воркшоп можно и без регистрации.
Registration is optional for workshop.
Мы вас ждем в 15:50. Всем привет! Мы готовы продолжать нашу конференцию Back to Back. И следующий доклад будет посвящен замечательной технологии SIMD, что значит Single Instruction Multiple Data. Это технология, которая позволяет ускорить ваши программы в 8 раз, как минимум. Доклад называется Google's Highway Library for SIMD-programming. И его прочтет Ивица Богославлевич.
Dear friends, welcome back. Dear friends, let me shortly introduce Ivica Bogoslavlevich, a performance engineer at Johnny's Software Lab. This talk is about SIMD and Google's Highway library. So I guess that's enough because we have Ivica here and he knows better about this library to tell you more. So welcome. Let's welcome him one more time.
Great.
Awesome. Today we're going to talk about SIMD programming. Question for everybody: who has written at least did some kind of vector programming in their lives? Okay, and who does it regularly? Yeah, 2 people. Okay, it's expected, so it's fine. So just a short note about me. My name is Ivica Bogoslavlevich, and here it's written in Russian. Yeah, I work most of the time I worked as an embedded engineer, and I have 15 years of experience in the domain of embedded systems and software performance, and I have this Johnny Software Lab blog which talks about software performance, and you can see the link to the Johnny Software blog here at the footer of this presentation. So what is the content of this talk? The goal audience, you don't need to have any previous experience with vectorization, so I'll explain everything as we go. So first we'll introduce what the vectorization is and how does it relate to software performance. Then we go to Highway. So Highway is a Google library that allows you to do vectorization in a very nice and convenient way. Then followed with real-world examples and some discussion and summary. So I hope you're ready. So let's start. So here is an example of vectorization. So what's the deal with vectorization? So many modern CPUs offer instructions that can process more than one piece of data in a single instruction. So here is my loop. C of I equals A of I plus B of Y. But when the compiler translates it, it might decide to use vector instructions. So instead of loading just one element, it loads 4 elements of vector A and puts them in a vector register. So I see that 4711 was loaded from the memory and put in the vector register inside the CPU. And then from the address B plus I, the compiler loaded four values, 3280, and put them in the second vector register. And then it executed the add instruction, the vector add instructions, which added together four values from this register to produce 4 results. And finally, 4 results were stored back to the memory. Okay, before moving on, a few things about vector registers. So vector registers inside CPU, they can hold more than one value. So typically it can be 4, 8, depends on the type. And also they can, but each vector consists of lanes. So in this case, a vector register has 4 lanes, so it can store 4 values. And the lanes are typically numbered from 0 to 3. So from 0 to n minus 1 if we have n lanes. So how does vectorization go? So many times when you write out your loop in your code, whether it is C++, maybe Java does vectorization as well, Rust also, the compiler can recognize certain patterns that are vectorizable. And for example, if your pattern is correspond to STD transform, so you just have input arrays and you produce output results with addition, multiplication, square root, whatever, then the compiler can vectorize that automatically, so you don't have to do it. Also the STD reduce, so for example, reducing whole vector to one single value. Let's say you are adding elements of a vector to to produce the sum. So this is, in principle, compiler can vectorize those as well. Now, the thing with vectorization and the compiler is that compilers many times, they rely on pattern matching. And sometimes this vectorization either will not happen or it might break. For example, you have a for loop, and then it worked really nice. And then inside that loop, you added a debug output, and then the performance collapsed. Even if that output is protected, like if debug, it will collapse because the compiler automatic vectorization in that case collapses as well. So what happens with compiler vectorization is not enough, so we rely on manual vectorization. And the manual vectorization happens with these compiler intrinsics that all vendors offer, like Intel, ARM, but also RISC-V and others. MIPS has their own. And here on the left side, you see like the original loop. And you see that loop the increment of the loop is by 1. But then on the right side, what you see is that the increment of the loop is by 8. And I see that this intrinsic called load underscore PS, MM256 load underscore PS, it reads 8 values from address A plus I and stores it in this vector register. So this M256 type, this one here, it is a vector register, and it can be stored in the vector register in the CPU, sometimes in memory, really depends. So the load intrinsics loads that value, and the add intrinsics adds them together to produce 8 results. And finally, we have this store, which stores it back to memory. Now, first time, if you've seen this for the first time, you will be overwhelmed. What's this, and why these underscores? Why it's so complicated? Does it really needs to be? But the things are as they are, so we cannot do anything about them. But Highway tried to do something. So what's Highway? So that was a short introduction to vectorization, and you've seen the problem with these intrinsics. So they are really clunky to read, and also they're not portable. So if you write for, let's say you're writing for AVX, for Intel, and you want them ported to ARM, to Neon, it doesn't work. So Highway is a vectorization library developed by Google, and it's the most mature one that we have right now and the most used one. It is written in C++, and it relies heavily on templates. It can be header only, so if you're just using intrinsics and you're not using any functions from the library, it can be header only. But if, let's say, you want to do some debugging or, I don't know, whatever, then in that case, you need to link against it. Now, it tries to solve two biggest problems of vectorized programs when written with intrinsics, that this is readability. So we don't read this clunky mess here, as you've seen, and also portability. So we can write it once and then have vectorized, the same vectorized code also on Neon, on RISC-V, whatever. So how does the library do? What are the main properties of the library? Well, first, that the library is vector length agnostic. So the thing is, when I showed the example, I said, well, we are processing here 8 floats. Well, the library doesn't assume that the architecture has 4 floats or 8 floats or 16 floats. So it's vector length agnostic, and it's some kind of constant that will be resolved either during compile time or runtime. Now, the Highway library has a lot of vectorization intrinsics available. And another really nice feature is called dynamic dispatching. So what does the Highway? Highway takes your implementation and then compiles it once for SSE, which is like the oldest vectorization framework, vectorization ISA, and then for AVX, which is like the most common one, and then for AVX 512, which is the newest one, but probably not available in most places. And then when you're running your program, it will dispatch it will pick the most efficient one and use that one. So this is like really big stuff in the library itself and very useful. And finally, what Highway allows you, it allows you to mix Highway intrinsics together with native vector intrinsics. So most of the things are exposed. So the Highway itself, Highway intrinsics are just light wrappers around the native intrinsics, but some intrinsics are not exposed to Highway, and sometimes you need to do like a little bit of plumbing here and there to have everything work perfectly. Okay, so I explained the code on the left side, so this is the AVX version, and now on the right side you see the Highway version. So first the thing, let's see what are the differences. You have this const HN scalable tag float D This variable, let's call it like that, it's not really a variable. It doesn't resolve to anything at compile time. It's just a thing that you pass around these intrinsics to let them know the type. So it will know this load D is a type float and not double, for example, in this case here. So you see it's pad here, here, and also here. So this is what it is used for. The second here is that in the AVX it increases by 8 because we know that on AVX we have 8 floats in a single register, so 8 lanes. And here I have this call to lanes of D, which means that the lanes is not known at compile time. So for example, on Neon, these lanes will be 4, but if you compile it for AVX, it will be 8. And if you compile it for AVX 512, it will be 16. So next you see the intrinsics, and the intrinsics are really readable. So you have this load, and store, which is okay, fine. And the last thing is that for addition, subtraction, multiplication, and so on, you don't need to remember any intrinsics. You just use overloaded operators. So operators like plus, minus, multiplication, and so everything is overloaded, so you can do it. You can write it really nicely. So you see it on the left, and you see it on the right. So the difference is quite big. Any questions? Okay. Okay, so here is a more convoluted example. So if you see on the upper right part, so what it does is, if a of I in green text, so if a of I is greater equal than 0, then result of I is square root of ai, else result of I equals 0. So this is implemented on a for loop. So the for loop starts there, and also implemented with vectorization. So this if is running on a loop. So what do we see here? I see scalable tag. So this is the thing that tells you I'm working with floats. I get the number of lanes. Now, because I'm working in vectorization, so it might happen, let's say my vector size is 8 lanes, but I'm processing 10 values. So I'm going to do one iteration, which is a vector iteration that processes only 8 lanes. And then I'm going to do another iteration, which is a scalar iteration, not in vectorized code, that processes the remaining 2. And this is how I calculated the end of vector iteration. So I take n divided by lanes times lanes, and I get rounded to the power of 2 of the number of lanes. So if this is, let's say, 16 divided by 8 lanes, so it's 2 multiplied by 8 lanes, it's again 2. But if it's 17, it's also 2. Because the last lane, which is here scalar tail that is missing, will be processed in a scalar loop. Okay, so next I'm defining here 2 types, vecf32 and maskf32. So this is a vector register. So we don't know how many lanes it have. Let's say it has 8 lanes, and it stored 8 floats. And here this is a mask register, so type of a mask register. I'll explain what mask register is a little bit later. It also stores 8 values, but not the floats, it's just 1 bit per lane. We'll see what it is. And the last value here, this one is 0. So what it says, I have zeros in all the lanes of my register. So it can be 8 zeros or 16 zeros depending on the architecture. Okay, so here is the loop. Loop increases by lanes. So I do load A. I calculate square root of A. So I load A. I calculate square root of A. So what you notice here is that I do calculation of square root regardless whether A is greater or smaller than 0. Some lanes in this result will be not a number. For that input is greater than less than 0, the output will be not a number. Now this type mask f32, it calculates the mask. So mask is, you see that up there I have a of I greater or equal than 0. So I'm calculating for 8 lanes. For each lane, whether it is greater than 0 or not, or smaller than 0. So I do this calculation for 8 lanes in parallel, and I get 8 results, 8 bits, 1 bit per lane. So 1 bit per lane will tell me if the bit is true, then I'll have that this comparison is true. Otherwise, it will be false. And here's the final trick. So I call this intrinsic, calls if then else. Okay, I give it my mask, I give it a square root result, and I give it 0. And what it will do, depending on the mask, if the bit in the mask is 1, the corresponding lane will come from square root. Otherwise, the corresponding lane will come from 0. And finally, I have my store. So is this clear? Okay. So this is how you do. In vectorization, you cannot, for one, I want if for this piece, so for these lanes I want to do square root, and for this one I don't want to do anything that doesn't exist. You need to evaluate both the body of the if and body of the else, and then use this if then else to pick the one you want depending on the condition. So two types are really important, this vec F32 and mask F32. Okay. Any questions? Yes? Okay. Okay. So, so the question is, if we have a reminder that's, let's say, 6, can we do like with the smaller lanes vectors? Yes, it can. We can, but it's out of scope of this lecture. It's possible. Yes.
All right.
Okay, let's go through Highway operations. So simple operations, this is like where Havens is the brightest, I would say. So overloads for many standard arithmetics, plus, minus, multiplication, divisions, logical operations, so AND or XOR, whatever, and it results in a very readable code. Here is an example of square root of A times A plus B times B. And if you see on AVX, this is how it looks on AVX. So you calculate, call mul intrinsic A, then mul intrinsic B, then add intrinsic on the results, and then square root the intrinsic of the whole expression. So this is on AVX, and Neon follows exactly the same pattern. So it's again mul, then you call add on those two results, and then you call square root on everything. And this is on Highway. So just square root A times A plus B times B. Now conditional execution, we already covered those. The thing is that here is a C implementation. If A greater than 0, R equals square root of A, else R equals 0. So here is how it looks like on AVX. So you have this blend V intrinsics, which implements that if then else. And then if then else will pick between set 0, so it's all zeros, and square root of A, so the calculation of square root of A for all lanes. And then you call this compare intrinsics, which again has all this here, A and set 0 and so on. On Neon, very similar story. So instead of this set 0, we call this V dup Q and square root A and so on. On Highway, so there are like several implementations. This one like the most flexible one. So I calculate 8 greater than 0, and I get my mask, my predicate result. So it's 1 bit per lane. And then I feed it to this intrinsic, and then I pick between square root and 0. But also Highway has like several other ways. There is also if then else 0. So it just you give it a condition, you give it a result in true, and if false, it sets everything to 0. And there is a third way and fourth way also. So you have this mask square root. You give it condition, and you give it the value you want if the condition is false, and you give it A, and it calculates square root of A. And the final way, which is this one. So just give it a condition, an A, and it calculates square root only for those places where condition is true, for all those lanes where condition is true. So the question is, why do we have so many? And the answer is, well, sometimes you want flexibility. So maybe we don't want to set 0, maybe we want to set 1. And also like this intrinsic here, on some architectures, it translates to one instruction. Not on all of them, just on AVX 512 or SV from ARM, it translates to one instruction. On AVX 2 or maybe SSE, that translates to several instructions. So the rule of thumb is when you are working with these intrinsic, you are looking for the most specialized one. So the most specialized one, because that one ideally can translate to any architecture most efficiently. Okay? Because, for example, maybe this one will be very efficient. This one and this one will translate to the same thing on AVX2, but not on AVX 512. Okay, predicate mask, I explained already those. So we have two types. One is the vector values, vector of values. So we have eight lanes of floats, and then you have 8 lanes of bits, and bits are the results of comparison. Now the thing is that you can, with the mask values, you cannot add them together, right? No point. But you can use logical operations. So you can take 2 masks and calculate and, or whatever. And finally, you can check bits in bulks. So, for example, I have 8 bits, and I'm checking whether at least 1 bit is set, or if all the bits are set, or any bit is not set. So imagine you're like, let's say I have a string, and I'm looking for character A inside the string. So how do I do it? So I take my 32 characters for my string, I load them into memory, and then compare them against a vector which contains 32 instances of A. And I just need to check that all the bits are 0. If there is at least 1 bit that is 1, I found my character. But if all the bits are 0, I can just move on to the next iteration. There is also all false, all true, and count true, and there are also other intrinsics as well. Any questions? Questions?
We will have a question session at the end of the speech.
Okay. So the next things are permutes and shuffles. And these are special instructions that rearrange lanes in a vector. So here is an example of a loop that can only be implemented with permutes and shuffles. So this is conversion from ARGB to RGBA image. So how does it work? Well, I'm taking a packet of 4 bytes. So this is 1 pixel, ARGB, and then I need to put the one that is at position 1 to the position 0, and the position 2 to position 1, and pixel position 3 to position 2, and pixel at position 0 to position 3. So this is I'm just permuting stuff. I'm not doing any calculations. And Highway also exposes intrinsics for this one. Here you have an example of on AVX. So this is an AVX intrinsics. So the intrinsics itself is called permute for x64 underscore epi64. So the thing with these intrinsics, if you look at it like this, what's happy for? What's 460x? What is this shuffle? Yeah, it does like this. So you give it this 0032. So when you're reading this mask, you're reading it from right to left. So this is for lane 0, for lane 1, for lane 2, and for lane 3. And here, see, I have indexes 2, 3, 0, 0. So they're just read the other way around. And it calculates out of I equals in of index of I. So it will just do the permutes here. So what is at lane 0 goes to, so what is it at lane, and at lane 2 goes to lane 0, and what is at lane 3 goes to lane 1, and so on. So is this clear? Okay. So this is like a real world permute from AVX. epi64 is just working within 64. Now, with permutes and shuffles on Highway, there is a problem, and that is that AVX and Neon and also other architectures, this is where the architectures differ the most between how they implement them. So Highway had to adapt. So there is like a standard vector repertoire of shuffles. Some of them called interleaves, zips, broadcast, table lookups. I'll explain at least some of them a little bit later. AVX have additional intrinsics. These are called configurable intrinsics, where you can like give any mask and it can shuffle anyway. And these are not supported on Highway, they're not exposed. When it comes to permute shuffle intrinsics, there are 2 categories of intrinsics. One are called blocked, because the permutations are performed within 128-bit wide blocks. So imagine I have my vector, and let's say vector is 512. And then I divide my vector into 128-bit wide blocks. And all the permutes happen inside these blocks. There are no permutes that go outside to other blocks. So everything happens within these blocks. Now, what's the deal with this one? Well, first, when you're working with this kind of intrinsics, you don't care. So Highway guarantees that all vector lengths are a multiple of 128-bit. So vector size can be 128, 256, 512, 900 and something, but it has to be a multiple of 128. So this allows you to write vector length agnostic code. And the second thing is the AVX compatibility. Now AVX, as it was designed like 10 years ago, 15 now, it had this problem is that Internally, so AVX vector length size is 256 bits, but internally it's divided into 228-bit blocks. And if you do permutes that cross this barrier, so cross the blocks, move between blocks, these are typically 3 cycles. But if you're within the block and you're not moving around the block, then you are 1 cycle. So it's quite it's a visible improvement. So these are the blocked vectors, permutes and shuffles, and there are known blocks where permutations are performed across the whole vector, so you can take something from the end of the vector and put it in the beginning, and so on. I have an example here. So this example assumes there are 8 lanes in a vector. So the assumption is that there are 8, but this in normal highway is vector agnostic, so this compiles only on AVX. It doesn't compile on AVX 512. And I have this one vector which is h and iota. Iota is from 0 to 7, so I just give you the beginning. And the second one is from 8 to 15. And then I have this intrinsic called interleave lower. I gave it A and B, so it will take one value from A and one value for B, so 0, 8, 1, 9, 0, 8, 1, 9, 4, 12, 5, 13. So you see that these 4 values, they come from the lower part of A and B, and these upper values, they come from the upper part of A and B. So you see this doesn't cross the 128-bit block. They don't cross the block. Then you have interleave upper. So this one works with lane 0 and 1, and lane 4 and 5. The interleave upper works with lanes 2 and 3, and lanes 6 and 7. So you have 2, 10, 3, 11. So I don't see 2, 10, 3, 11, and then you have 6, 14, 7, 15. 6, 14, 7, 15. There are also other intrinsics like these shift left lanes. So I'm just giving you an overview of few intrinsics, not all of them. There are a lot of them, but just to see how it works. So these shift left lanes takes like the input, which is 0, 1, 2, 3, 4, 5, 6, 7, and then shifted left by one lane, and it copies. I don't know why it's called left. To me, this is right, but yeah. So you get 0, 0, 1, 2, 0, 4, 5, 6. So this one also works within 128-bit blocks. You have this odd even. So odd indexes lanes from A, and even indexes come from B. So I have 8, 1. How is it? Yeah, 8, 1, 8, 1, 10, 3, and then you have 12, 5, 14, 16. Okay, and the last one, which is probably the most interesting one, is called this table lookup lanes. So you give it the indexes like an array, so it's 7, 6, 5, 4, 3, 2, 1, 0, and you give it the input, which is A. So, and it will shuffle the vector based on these indexes. So it will go, in this case, it will reverse it. So originally it was from 0 to 7, and now it is from 7 to 0, 7, 6, 5, 4, 3, 2, 1, 0. Okay, questions? Okay. Okay, so this I think covers the topic of the intrinsics. So you see it's not difficult. Permutes and shuffles are the things probably the most complicated stuff in vector programming, because you need, as long as you're doing the same operation on a single lane, it's just like normal programming. But when you introduce permutes and shuffles, then things get complicated. Yeah, so, and this is like the permutes and shuffles, at least in my experience, this is what the most people probably struggle the most. But this is also the thing where the compilers are the most problematic. They don't, as soon as permutes and shuffles are needed, somehow they just avoid it, they don't figure out their pattern and so on. So real world experience. How does it work in messy real world scenarios? So I'm sharing some experience that I had, and I'm intentionally focusing on the problematic parts, not the parts that work correctly, because the parts that work correctly will not surprise you. Those parts that work bad will surprise you. So one is working with interleaved data. The thing is that vector instructions are designed to work with an array of simple types. So I have like array of floats or of array of int32. but many times data is stored in interleaved format. So I have like this complex number which has float part and imaginary part. And I have this, for example, RGB, which has red, green, and blue. So it will be stored red, green, blue, red, green, blue. So if you look at the memory layout, it looks like this. So complex 0 will be real, imaginary, real, imaginary, real, imaginary. So what happens when you load that data from the memory to your vector register? Well, even lanes are real part and imaginary lanes are in, real values are in even parts and imaginary lanes are in, imaginary values are in odd lanes. So what happens is that, does it work for you? Well, the answer is you want all real parts to be in one vector register and all imaginary parts to be in another vector register. So it doesn't work, this doesn't work really great. And you need to do some permutes and shuffling. And Highway makes working with interleaved data breeze. It's really simple. There is this load interleaved X, like on load interleaved 2, load interleaved 3, store interleaved 2, so, and you see how it works here. So I have two A real and B real, A real in E imaginary, B real and B imaginary, and I just call this load interleaved 2, and I give it my pointer to A plus I and B plus I. And voila, what happens is that I have that ARE contains all the real parts and AEIM contains all the imaginary parts and so on. And then I can calculate, this calculates the multiplication of two complex numbers. And I can store interleaved 2. So what this store interleaved does is takes my data, which is not interleaved, and interleave them. So you get the similar, you get this layout. Now, does this work? Well, it depends. On Neon, it works really nice because Neon translates this load interleaved 2 and store interleaved 2 directly to one instruction. So it's super. On AVX, there is no such instruction, doesn't exist, so it needs to be emulated. So it's emulated, you do like 2 loads, you load 2 vector registers, and then you do some permutes to put real in one register and all the imaginary parts in another register. And how does it cost? What's the cost of it? Well, load interleave 2 and store interleave 2 emit 2 load instructions and 4 shuffle instructions, total 6 instructions. And the thing is, those shuffles that are emitted, they cross the 128-bit boundary. So they're not the most efficient shuffles that we have. The thing is that on AVX, you can avoid crossing 128 binary. There is a trick how to do it. And this is essentially the idea. So I call these intrinsics, this shuffle PS with these values. So from original layout, which is R0, I0, R1, I1, R2, I2, R3, I3, I get R0, R1, R4, R5, then R2, R3, R6, R7. And for the imaginary, it's really similar. So I get I0, I1, I4, R5. So the question is, why are we doing it like this? It doesn't make a lot of sense. Yeah, but when you think about it, it doesn't make a lot of sense. Ideally, we would like R0, R1, R2, R3. But if we do a layout like this, we don't cross the 128-bit boundary. And when we're done with our computation, and this is our results, and now we want to store them interleaved into memory, we use these 2 intrinsics. So we get R0, I0, R1, I2, I1, R2, I2, R3, I3. So what happens here now? Well, what happens here is because our data was originally stored like this, our results can be interleaved without crossing the 128-bit boundary. And so, do we care? Well, this is the performance comparison on AVX. If we have naive highway, it costs 1.13 seconds to run, I think, 500 million computations. But if you use custom, so I wrote load interleave AVX using native intrinsics, then I go to 0.67 seconds. So the speed up is almost 2 times. And Highway does vectorize it, but doesn't vectorize it efficiently. Is this clear? Okay. Yeah, some people, yeah. The gist of it is. And the next thing is matrix transpose. So I have a matrix transpose operation here. So matrix transpose in vectorization. When I say matrix, I mean like a fixed size matrix, let's say 8 times 8 or 4 times 4 matrix. And I want to transpose. So I have 4 lanes in 4 vector registers, so in total 16 values, and I want to transpose them like this. Now, this operation is a very important operation for other things. So for example, outer loop vectorization. I'm not going to talk about it. Yeah, so we need it a lot. And the problem with this one is it's not on AVX, on Neon, AVX, it's not too complicated to implement. But the thing is, if we have a vector agnostic vectorization like Highway or maybe SVE, then things get much, much more complicated. So how many registers do we need to allocate? If we want to 8 by 8 rotation, do we need 4 or 8? So the number of registers that we need to allocate is a compile time constant. The complexity of rotation depends on the matrix size. So small matrices like 2 times 2 are relatively simple to rotate, but a matrix like 16 times 16 or 32 by 32, you need a lot of instructions to do that rotation. I haven't managed to implement it, so if anybody wants to do it, they can try it out. We talked about the scalable tag, so I thought it tells that it is float, but it doesn't tell that it's float only. It also tells you that this is vector length agnostic. There is also fixed tag, whose size is known at compile time, but it might happen that particular architecture does not support it. Yeah, so any questions? Okay. The third example that was really like problematic was this fixed point multiplication. And on the right side, you see fixed point multiplication. What does it do? You have an array of int 16 values, and they're like 8 bits are before the decimal comma, and 8 bits are after the decimal comma. So what you want to do, you want to multiply those 2 values, and the multiplication is done. First, you take A and B and convert them from 32 to 60, from 16 to int 32. Then you do the multiplication. Then you shift the result by 8-bit, and finally cast it back to int 16. So this is how fixed point multiplication is done. So yeah, so what's the problem with this one? So the naive implementation would be like this. I take my register, which contains, let's say, 16 int 16 values, and I convert it to 2 registers, each one containing 8 int 32 values. Then I do the multiplication, then I do the shift, and then I convert them back. So this is how, like, naive way. If you never did vectorization and you don't know how it's done on Neon and AVX, this is how would you do. And you see, you get really nice code. So just let me explain before moving on. So the thing is, when you're converting from a smaller type to a larger type, you will need to increase the number of registers. So I have 16 int 16 values, and I'm converting them to int 32. Now I get 16 int 32 values, but to store them, I need 2 registers. So I'm going to convert individually the lower part and the upper part. So here is an example. This promote lower 2 and this promote upper 2. So this promote lower 2 takes the lower part of A, which is int 16, and converts it to int 32. And this promote upper 2 takes the upper part of A, so only half of the lanes, and convert them to a bigger type. Is it clear why it works like this? Now the deal with this promote lower 2 and this promote upper 2 is they also cross 128-bit binaries on boundary on AVX. They do cross it, and they're slower. And then we do multiplication, then the shift right, and this narrowing back is a little bit tricky because there is not a big bit casting, like CCast doesn't exist, so you need to do some bit casting and then this truncates so on, but it's fairly okay. But the deal with this one is this is not the most efficient implementation either for AVX nor for Neon. So how do they look like? So the thing on Neon is that you have an instruction that multiplies and widens, so multiplies and promotes. So it multiplies 2 16-bit values and promotes them to 32-bit result. And you see on the right side, there are 2 intrinsic. One is vmul S16, and the other one is vmul high S16. So this vmul S16 takes the lower 64 bits of the register and converts them to 128-bit result. And the other one does the same for the higher part. So it's multiplication and promotion. So 2 operations in one intrinsics. And then also there is intrinsic called shift right by 8 bits and narrow. So it takes 32-bit lanes and then it converts them to 16-bit lanes. And of course you have going from 128-bit register to 64-bit register. So what does it do is you have this result low, so it will give you the int16 x4, so 4 int16 values in register. And then you have this shift right narrow high, which takes low high and shifts them and then combines the result low and of this operation of shifting and narrowing, and then you get the result. Now this happens, this is 1, 2, 3, 4 instructions. And originally we have 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say. Is this clear? Any questions related to understanding? So just remember that Neon has for multiplication, it has a multiply and widen, and for shifting right, it has shift and arrow or demote. So you get this really nice code. And on AVX, the thing is the problem of crossing 128-bit boundaries. So this is still exists. So there is a more efficient implementation that doesn't need this first to promote and then to multiply. It uses these 2 intrinsic called mal low and mal high. And it's really weird. It's really weird and really bizarre. And this is like the workarounds and hacks you need to do to avoid lane crossing. So let's say my A is 0, 1, 2, 3, 4, 5 to 15. And B is all ones. So I call mal low and I get lower 16 bits of the results. So the result is 32-bit, but it's stored in 2 registers. Lower parts of the results are stored in the 1 register, and the higher parts of the results are the result of this small high, and they're stored in a 2nd register. Okay, so this is the weird part. Like nobody would expect it to work like this, but it does. So what then you need to do? Well, you have this lower and upper part, and you need to join them together, right, to get 2 32-bit results. Again, I'm using this unpack low and unpack high, and I get 0, 1, 2, 3, 8, 9, 10, 11. So these are the lanes, the results. So they're not packed consecutively because this tries to avoid the crossing of the 128-bit boundary. And finally, when I have my results, then the deal is that on AVX, you don't have an intrinsics that converts the int32 to int16. What you actually do is you use the shuffle API. So you take your register, which is like 32-bit lanes, and then you reinterpret it as though it has 16-bit lanes, and then you're just picking odd parts of that one, or even parts, whatever. And this is how it's done. So this is what you get from this big result. You get 0, 1, 2, 3, and then 4 zeros, and then 8, 9, 10, 11, and then all 4 zeros. And from this register, you get something similar, and then use OR on them, and join them to get the result final. Now, this is the code. It essentially uses the same thing, what I explained here. Now, the thing is, why did I explain it? Why does it matter for us? The numbers are actually, what's the deal with this one? So AVX went from naive implementation, had 0.52 seconds, and this one, which is improved, had 0.34 seconds. On Neon, we went from 4.85 seconds to 3.7 seconds. So again, the difference is substantial. I mean, you can say that the difference is not that big, but when you're already doing vectorization, do it properly. Now, luckily, Highway allows you to write, you can write this, how it's called, fixed point multiplication as like a function, and then you write your specific AVX version, a specific Neon version, and another which will work everywhere else, and then you can do the compiler and it can do the other stuff. Any questions here? So my question for you is, have you understand at least the gist of it, not the essence, not the whole thing? Okay. So you see, if you're working with AVX, you'll meet this kind, I'll call it crap, all the time. So this is the normal thing, and AVX happens very often. So these are the three real-world examples that I have most problem with. Another problem is that like when you're actually working with a library, it has like some kind of configuration issues. So it has some quirks that can lead to slowdowns or maybe unexpected behaviors. Like I compiled everything with /mavx2, and it wasn't working correctly because it admitted the SSE version. So, and if you want to AVX version, you need to provide mark Haswell and MAES, then you'll get the AVX version. For example, I compiled with SEM CPU. I was working on Raspberry Pi, so I compiled everything with Cortex A72, which is Raspberry Pi 4 CPU, but it didn't enable Neon. It enabled Neon without AES. So when you're working with these macros, it doesn't work really well. Like this dynamic dispatching, I tried that one also. It works, but it's a really pain to set up because it takes your code and compiles it like 5 times with different flags. So you have 4 or 5, let's say 5 implementation of the same functions. And if you mix at least a little thing with templates, it just breaks. You get like this huge compile output with all these errors, and you need to figure them out. Everybody who has worked with templates know those. Yeah, but you take like the example from the website and you copy it really carefully and it works. Yeah, so that's it. Conclusion. As far as readability is concerned, really great readable code. Once you introduce permutation shuffle, it stops being readable, but it's still more readable than AVX or Neon or SVA, whatever. So it's a very good readable code, especially if somebody is like new in the team and they start working on it and it just doesn't, you know, like you see this clunky, complicated intrinsics, just doesn't work. As far as portability, it's good, but not perfect because you have these blind spots. There's some intrinsics are unsupported on all not supported on all architectures, therefore they're not exposed. Therefore, because they're not exposed, you are not even aware of them. So when you're programming with Highway, you still need to know the architecture underlying that you expect your program to work on if you want really good performance. And as far as ease of use, that's like probably the worst thing. So that you need these templates and need to, you know, when problem happens, you get like this huge output of templates and not working and so on. But apart from them, I would recommend this thing for those who do regular vector programming. That's it. I just want to do like a small announcement. I work for Johnny Software Lab, and we organize the AVX and Neon workshops. And actually, the example that I gave here are from the workshops. And in 16 hours, you learn vectorization from the ground up, so you don't need to know anything. And we go through basic intrinsics, advanced intrinsics, and we learn how to vectorize for loops, while loops, loops with early exits, like loops with breaks, or loops with return. Then we go to common vectorization patterns. We learn how to remove vectorization inhibitors. And we learn how to vectorize binary trees, search tree lookups, outer loop vectorization, and finally, when we get to the point of making everything, getting to the peak performance, like optimization for the memory subsystem, and how it's called, the instruction level parallelism. Okay, that's it. Thank you very much.
Thank you very much for this deep dive into hardcore SIMD instruction talk. I enjoyed it very much because I love SIMD.
I saw you sleeping.
Thank you.
I did saw you sleeping.
Okay, now it's time for questions, please. Who have questions? I see a lot of questions, but we have not a lot of time.
But we ask questions one by one. We don't vectorize them.
Давайте я начну. Just simple, maybe not even a question, just simple notice. I have worked with Intel Intrinsics for just several months, optimizing some work, and have found that the most problem is not how you write intrinsics, but wrappers around this code. For example, if vectors are randomly located in memory. For example, you are just using some ML embeddings which are just vectors randomly thrown in memory. Then you need to prefetch memory, and such libraries need to adapt to this. And for example, AVX have just quite a nice prefetch intrinsic. And does this library have some prefetch?
Yes, yes.
Okay. Second one is just, it looks like since hardware is different, it looks like any generic work on top of it will always have such pitfalls we have seen before. And from my just experience, it looks like you need to make different template versions of functions for different vector sizes, because if you just using generic loops, they work very badly, because every time you need to do condition that loop could be finished with this vector size. And if you know the vector size from the template arc or something like that, then all these conditions could be thrown away from the code, and all the functions from different bodies of the cycle will just interleave with each other, introducing better performance. So probably you could just try it yourself.
So I don't know what's the question.
It's just not the question. It's just idea that such libraries must be going with additional experience on top of it, that you need to use templates to get the best performance, not only from instructions themselves, just by organizing the code.
Kostya, I'm sorry. Today, our speakers give only one talk.
Sorry.
So, okay, last question. Unfortunately, we are running out of time, but let's ask. We are going to let you ask the last question.
Okay, thank you for your talk. So in C++26, we will have SIMD in the standard library. So is there any advantage to using Highway compared to the standard solution?
So I haven't tried SIMD, but I heard some feedback. It's like really in the early stage. So a lot of stuff is not yet exposed. But again, I cannot give you a good answer. So you need to look it up yourself. The Highway is like at the moment, it changes. It can change. There were things that were really important 4 years ago, not anymore. So I don't know.
There is a very nice publication about SIMD, and unfortunately, according to that publication, it sucks as many STD data structures.
It would be really shame if it doesn't develop further and becomes the standard part of the library. It would be.
Okay, can I ask a small question? Why we have overhead there? Because I expect from such libraries that it will be compiled into the same processor code as we can write manually. Why we have overhead?
We don't have overhead in the sense that the library introduces some additional instructions they don't get. Like the compiler is really good at optimizing and taking templated code and optimizing away instruction calls. What we do have is like if you're just writing generic code and you're not putting a lot of thought into it, what happens is at the end you won't get the performance that you might expect, or they can be elsewhere also. So the Highway itself, it's not like vectorization for beginners, far from it.
Unfortunately, we can't let you go until you show QR code.
Sorry?
We can't let you go until you show QR code. And people will not greet you, will not applaud you until they took their phones and ready to talk.
Boss says.
If you want applause, they... Thank you much for your talk. It was very interesting. So we are heading our last but not least talk. It's a great topic. It's microseconds in network code by Artur Solovyov. Artur Solovyov is senior engineer, and he is going to tell you how to squeeze last microseconds from your Linux network stack. Let's applaud Artur.
Уже не первый раз выступаешь на нашей конференции. Доклад называется «Микросекунды в сетевом коде». Артур, тебе слово.
Спасибо, Георгий. Thank you so much for coming again. So you hear me, you see me. If you don't hear me, please raise your hands. Not on the speaker. So someone here to fix it. And now I should be. Now you should hear me, or you don't. Got it. So this microphone scaled up as well. Check, please. This one or this one? Okay. I actually thought it would be the head microphone and kind of lost for a little bit. But you know what? Yesterday I've been on the test run, and this microphone shut it down as well. And I've been using hand microphone, and I've been cursing everything and everyone, because you need to hold that in a constant distance from your mouth and so on and so on. But I'll try to say my speech as it is. So we're going to talk about microseconds in network code, as people have already announced 2 or 3 times. But first, a few things about me. I will stay short and simple. Name is Artur, software engineer and mentor. I'm also experienced in trading and optimizations, so we'll gladly discuss it on the after party or just in my DMs. I will have a slide with contacts later, so you can slide, well, you know, into my DMs later. But now we need to start. So about this speech, please read those rows, because I will not be saying the same. The thing is, our problem is to handle a lot of network connections with different requirements. Sometimes, for example, in algorithmic trading, we need the lowest latency. I will give you an example. When, for example, you own a stock, and you get an incoming market data update that this stock's price is falling, you need to sell it as fast as possible. And that is why you cannot allow yourself high latencies. So you need to get optimized for low latencies. Sometimes we need high throughput optimizations. For example, in high DPIs, balancers, front proxies, and so on. Someone here develops any of those things? Thank you. Excuse me? High deep packet inspection traffic systems, high load proxies, balancers, so maybe virtualization frameworks. So if you do, please raise your, yeah, someone keeps their hand, and that is why I'm here for that level of involvement. Yeah, thank you so much. Yeah, good. So you will get a few techniques today and an overview of approaches. Everyone else will just get an overview of techniques just for your general engineering, like, how do you say in English? Your engineering, let's say, overview. That's the problem of English as a second language. There are 2 levels of getting screwed up. The first one is when you don't remember the word, and the second one is when you don't remember how to explain that word. And the second level, when it comes, you know, you are completely screwed up beyond all recognition. And that is exactly my case. I just wanted to say I'm glad you're here, and I hope you'll learn something from my techniques. And the speech structure is 5 approaches, 5 network solutions. The first one is kind of a workhorse. The second one is deeper and more complex to support. The third and fourth one are the same. And the last one is a crazy extreme offload solution. So let's start with the naive one. Hello? Yeah. So naive solution. it's called EPOL here, although I am kind of lying to you, because, well, the solution is just a send-receive API, and EPOL is simply a multiplication mechanism over those millions of send and receive calls. So EPOL simply waits on multiple descriptors, and those descriptors are just send and receive socket API calls, and those API calls are getting through the entire machine. So including the entire Linux network stack, contracts, NATs, firewalls, and so on and so on. I don't exactly remember what Linux network stack does entirely, but I only remember that it's really slow. And the scheme is, get ready for that. Kind of overwhelming, isn't it? Well, good news are we are not going to get into that scheme deeply at all. Bad news are we are going to have a few more schemes. They will be slightly less complex. So start with the first one. And the scheme is about how packet goes in our machine. NIC on the top means network interface card. That means simply network card. RAM means, well, random access memory, your physical memory. Linux network stack is you know what, user buffer is you know what, kernel space is. Someone here doesn't know what kernel space is, please raise your hands. That is completely okay, although I'm kind of amused. I think someone from the outside raised their hand as well. And you all turned your heads as if it was Linus Torvalds, and I was like, here, it's Linus Torvalds here, hello, and you're all like, good. Okay, so getting back to our EPOL, how exactly packet goes inside the system? It goes from the network card interface to the physical memory. It gets copied through the mechanism called direct memory access. Direct memory access is when you simply, without CPU involvement at all, copy automatically from device's memory to the physical memory. And at the year it was developed, I think 1990 something like, 12th century. It was like a breakthrough, but now we are like DMA, okay. So today we are not even noticing that copy, although it has some overhead on our system bus, all those PCI Express things and so on. We just don't consider it because that's not a bottleneck. But anyway, let's leave here a note that copy of the packet happens here as well. And from the RAM, it goes to the Linux network stack. Linux network stack processes all of those firewall rules, network address translations. As I have mentioned before, I even have that somewhere on my list, but I don't want to address that. Let's just say it's slow and it's a huge involvement of some unnecessary code. So Linux network stack parses packet body, then it copies body to the socket's receive queue, and from the socket receive queue, it gets copied to the user buffer. So as you can see, there are 3 copies and extra copies, extra syscalls, because to address socket's receive buffer, you need to do a syscall. There is extra allocation in kernel, and allocation in kernel is always bad, because Linux kernel allocator, someone here knows what kind of delays it can introduce. In the worst case, please raise your hands if someone knows. I see no hand, and I see one. So how much? Exactly right. Namely, something more than, just a minute. A tactical pause to remind myself that Linux kernel allocator at worst case has reclaim between cores at 100 of milliseconds, which is huge because that could be tens of thousands of requests and that is a nightmare. And that is why we want to get rid of Linux kernel allocation as fast as possible. How, I will explain you a bit later. Now just remember, system calls, extra copies, allocations, kernel to user space to kernel space, DMAs, and so on and so on. And there's no way to get rid of all of that using only EPOL. And getting to latency numbers. Latencies could be as big as hundreds of microseconds on the path from the receiving network queue to the outcoming network queue. And you can use some patches to cut it, but still it would be something around, I guess, 100 microseconds in the worst case, or 120, doesn't matter, it still will be slow. Someone here understands why 100 microseconds is slow? Yes, exactly, because hundreds of microseconds times million, times 2 millions, and so on, that would be seconds user can notice. Big picture, big picture, B and P. B goes and then P, yeah. Big picture consists of too many small pictures, too many variables, and we need to optimize here and there. And today we're going to optimize EPOL, and well, honestly, we're going to throw it away, but let's say it like that. Yeah. The thing is, when you're trying to tune EPOL, your throughput shrinks as your latency shrinks as well. And that is kind of opposite directions. You can either optimize for high throughput, or you can optimize for low latency, which is what we are going to do today. So about EPOL tunes. Anyway, I'll cover them for a few minutes, just for you to know. So you can consider CPU affinity here when you bind threads to physical cores. That from the first side, it looks like it's not a bottleneck for the EPOL solution, but you can still do that, and that will give you some profit. So CPU affinity matters. But generally, you want to avoid CPU bouncing because of a pitfall named cache line bouncing. Cache line bouncing is when, consider an example where you are handling a packet from the user, and you are handling it on one thread. That thread is located on the CPU 0, and data caches are filled with the packet, with the client data. What happens next? Linux rescheduler reschedules it to the CPU 1. What happens with the caches? Old caches are unreachable. New caches need to be filled again. And while Linux scheduler reschedules your thread, pages from the page cache, yeah, exactly that. Pages from the page cache bounce between the cores, and that is why it's called cache line bouncing. And by setting CPU affinity, by mapping threads to your cores, you are getting rid of the cache line bouncing, and that is what really matters. One more pitfall here, which actually matters more, is system calls. So system calls, jumping between user space and kernel space and back, is for the first time it is an extra context switch, and extra context switch has its own overhead. But that is not why that's important here. Why is that important? Because data and extraction caches are getting completely erased when you are getting from the kernel space back to the user space. Someone here has an idea why? Yeah, kernel uses that memory and instructions, and getting kernel pages in data and instruction caches from the user side, that is a huge security breach. That is why page caches get erased and simple caches get erased. So each system call throws away your machinery completely, and you need to start from scratch. Someone remembers how much time it takes to address a cache line in physical memory without any caches? 200, exactly. And who told you that? Konstantin Oblakov. Exactly. Yeah, I remember that as well. And I just wanted to remind you, L3 cache could be something like 10-ish, like 10 to 20 nanosecond. So it will be an order of difference. That is why you need to utilize your caches wisely. And that is why you need to get rid of system calls. So another pitfall goes here. And multiport, I won't speak about it that much because multiport is simply when you have multiple clients on the same port and they're getting handled by multiple sockets. You pin those sockets to separate cores. Those separate cores use separate memory and so on and so on. You know, well, that's how horizontal scaling works, like shared nothing architecture, yada yada. You already know all of that. Yeah, if you have a problem, then simply add more cores. Now you have two problems. The first problem and the synchronization between cores. So shared nothing is when you don't have the second problem. Oh God, interrupts or busy polling. They are not that significant here, but I'll try to explain. But let me do one more sip of water to collect my thoughts. Even microphone tries to betray you sometimes, but I caught it and all good. Yeah, so interruptions. Interrupts are a signaling mechanism from the devices. Interruption, well, anyone here knows what interruption is? Okay, never mind. So interruption has its own overhead. Overhead is about doing a context switch, doing that thing with the interruption handler's registers table, doing that thing with the interruption handler executing its code. And although best practices for interruptions are to write handlers as small as possible, that is still some overhead. Instead, you can do a busy polling on your side. You can turn off the interruptions from the device and instead constantly ask it. For example, your network card can use interruptions for incoming packets, but instead you can do a busy poll, and in that busy poll you can ask, any packets here? Any packets here? Any packets here? Any packets? That will, spoiler, that will take all of your CPU load. So not so energy efficient. But at the same time, that will provide you with the lowest latency because at the very time the packet goes to the network interface, you will handle it. So choose wisely. Yeah, etc., etc. I will not bother you with code much, mostly because Boostagio kind of covers EPOL function entirely. And, well, Boostagio has EPOL as its backend, one of the backends. And the thing I wanted to highlight is from the C++ 17, we can get rid of, you remember how much kernel, Linux kernel allocator breaks things up. So you have an option to get rid of Linux kernel allocations by using your own. Pay attention to the string monotonic buffer resource. That's what we need. The allocation with buffer resource could be as simple as moving one pointer. And that's exactly what we need to do. The technique is called bump allocation, or at least that's what Java programmers call it. They also use kind of strange terms for things, but you need to know. And bump allocation is how that's called in Java garbage collector book as well. So book is quite useful, by the way. So maybe we need to borrow some names from Java guys here. So the advantages are you don't have any jitter here related to the synchronization between cores, synchronization between processes, and so on and so on. But at the same time, you need to know how much you want to allocate, and you need to know alignments. And no way you can get rid of that. So you need additional information to trade your versatile allocator for a much less versatile but much faster allocation option. And that's what we need as well. So about live examples. Well, what's interesting about live examples, you can see them on the screen, is they're good enough for 90% of applications. But at the same time, there's a downside. There is no room for improvement for another 10%. Simple as that. If you're screwed up with EPOL, you have not so much means to speed it up drastically. So to summarize, well, I want you to read it yourself. I don't want to say it out loud because, well, that would be boring. I just wanted to highlight latencies, hundreds of microseconds, and in the best case, that would be hundreds of microsecond worst case, but best case, worst case, yeah, whatever. But you cannot achieve much faster. And all of those packet copies, interruptions, system calls, caching validations, unpredictable allocations, etc., all of that hinders your work as well. So what to do, you'll ask? Go deeper, I/O Uring. The idea is, let me show the scheme first, I think that will be better. So on the previous scheme from the EPOL, it was a socket receive buffer and a user buffer, two different buffers divided by kernel space. And here it is one buffer, two buffers here, socket receive buffer and a user buffer. And only one here, in shared memory. So when something gets processed by the Linux kernel network stack, it automatically is available for user. No need to do system calls, at least with the right tweaks. So allocations are user managed, syscalls are turned off if you have the right tweaks, and I don't actually see what is highlighted here. Let me check. Extra copy kernel user. Well, yeah, obvious. No extra copies here. Yeah. Okay. So the thing is, we are getting rid of that extra copy, and we are getting shared buffer between kernel and user space, and that improves things drastically. And here I wanted to say about busy polling to clarify things a little bit. So a moment. Pause and yield and back off. Oh God, I need another. Well, sometimes things stop working, and that's the world we live in. But when it's your public speech and the thing that stopped working is your head, then things become a bit more sad. Yeah, but my head is now okay, and let's go. So busy polling is when we are constantly asking something instead of signaling. And usually it occupies the entire CPU. We are not doing exponential backoff, so don't pay attention to the third while block. We don't need that at all. And busy polling, is the technique which provides you the lowest latency. By the way, someone wants to know what pause is? Good. And I won't tell, just kidding. Pause is when, let's say you have a no-op on some busy polling spin weight, and you're doing one operation constantly. You're doing that once, and you're jumping back to it, and so on. At the same time, your pipelines in the CPU get hints that this is all you're going to do. And on the last iteration, when you're getting out of it, your pipeline gets blown up. It gets completely cleared. And pause is a kind of a no-op, which tells it's just a spin weight. Please don't bother my caches. Don't bother my pipelines. So the best practice is to use pause here. Interrupt coalescing. Well, there is a technique based on interruptions, there is a technique based on busy polls, and there is something in between. Interrupt coalescing is when you do, someone here remembers what TCP-Nagel algorithm is? No? Okay, never mind. I'll explain. So interrupt coalescing is when after the first interruption, you are turning interruptions off. But how exactly that works, you will ask? What if we lose some packet? Never mind. It's just we turn off interruptions and switch to the busy polling mode. We ask device ourselves, are there any packets, any packets, any packets? You've got the idea. We fill some batching buffer, and only after that we turn on the interruptions and continue working. So we use interruptions for initial signaling, and after that we use busy polling for batching, and that way we win on the general high throughput. So yeah, best throughput by high latency jitter. Why high latency jitter? Because there is no way we're going to figure out where the packet is, at the start of our buffer or at the end. So those two packets will have significantly different latencies. Just a thing I thought you need to know. So about I/O Uring tweaks. I said that is zero copy, but you know I kind of lied to you because well, I/O Uring supports zero copy, but it doesn't do that well. And you need to keep an eye on zero copies. How to do that? Turn on feature called I/O Uring send ZC report usage. That means after each send or receive, you'll get a notification whether zero copy happened or not. And if it didn't, well, that's bad news. That means you need to go straight to the AFXDP, the next solution. Just kidding. Let's consider other tweaks. So you need to enable busy poll queues as well, because by default, I/O Uring works on system calls. If you want to ask me why, I don't know. It's just if I wanted to work with system calls, I would have took epoll. But for some reason, it works like that. You need to do a separate option. As far as I remember, that is I/O Uring setup as qpoll, but I don't remember. And that option turns on the separate Linux kernel thread, which constantly polls your user buffer for incoming updates. And when it gets them, it instantly processes them. Oh God, processes them, giving you the best latencies. Yeah, well, as I have said before, English is a second language. That happens. Yeah. And one more thing, shared kernel to user buffers are a thing you do not get the best control of. And that is why errors here could be really strange. On those SIGBUS, inval, faults, you do not always know what's happening, and the debug is painful. Syscalls already mentioned that. About code. Again, won't bother you with code. The most interesting things are going to be after that. And I just wanted to say there are a few people, including that Carter Lee guy, who have done wrappers around I/O Uring, and those wrappers have Boostagio-like interface. So if you want to switch from epoll to I/O Uring, you'll get some initial ground in terms of how to use it without like learning all the I/O Uring from scratch. I'm getting kind of tired of those real-world applications because each time it's the need to explain how exactly things are being used. And why exactly PostgreSQL or QEMU use I/O Uring? Not because of network, because as I have said before, I/O Uring doesn't win that much. They use I/O Uring because it enhances disk subsystem much, because I/O Uring knows how to utilize disk without extra copies. And that is what you need for Postgres, for its write-ahead lock and compaction of sorted strings or something like that, whatever. And that is what you need for QEMU for disk virtualization, to speed it up, because, well, virtualization has its own overhead. We want zero overhead. QEMU uses I/O Uring for zero overhead. Let's go next. To summarize, so from the first glance, it looks like there's no extra copy and no syscall to copy. But bad news are there is a copy, there is a debugging, and there is a syscall if you don't tune it properly. So as you might have realized, I don't like that approach that much. So AFXDP, much better, chef's kiss. So The thing is, AFXDP is a choice between using kernel network stack and not using it at all. And the thing is, you decide. And also that thing on the right called eBPF. What is eBPF? I need to stay here a little bit because eBPF is a technique which allows you to execute some change in code in the kernel at runtime and patch your kernel in runtime without rebuilding it. So that is eBPF is kind of a virtual machine inside Linux kernel which operates kind of a Perl-like code, and that code is sandboxed. So long story. I mean, you always can patch AFXDP with your eBPF code and make it redirect some packets through the Linux network stack and redirect some packets to your own stack. And that is why AFXDP is a cool approach, because that is a versatile bypass. So about the scheme, do we have EPOL scheme here? Yeah, get back to EPOL scheme, a lot of kernel, a lot of copies. And here it goes from the network queue straight to the shared kernel to user buffer. Please read this slide. Good. Okay, so we have realized we can use AFXDP to selectively bypass the kernel. And what would be the latency numbers? Now get ready for that. You remember for EPOL, it was something like 100 of microseconds. No, I want experiments, please. And here latency is 6 to 7 microseconds. An order less. And the jitter is not that bad. Jitter is something like 1 microsecond. So, like, as I have said before, chef's kiss. But a few pitfalls to consider. One of them is you need to consider receive side steering. Receive side steering is when, let's suppose you have multiple packets from multiple clients, and you want to share them between your codes, between your cores. What would be the best choice? Distribute them uniformly but randomly, or assign one client to one CPU? Who thinks it would be better to assign one client to one CPU? Exactly. Yeah, I appreciate your involvement, folks, and yeah, I agree with you completely. So how exactly do we do that called receive side steering thing? We take hashes of the client's IPs and ports, and those hashes are becoming CPU indexes. Well, actually, before that, they are becoming network queue indexes, because network card has multiple queues for RSS. Then they are becoming indexes for the physical memory queues, because physical memory also has multiple queues. So it goes one-to-one from the network card straight to the physical memory, and then each physical memory queue gets handled by one CPU, dedicated exactly for that. So no cache line bouncing, no cache line pollutions, and so on. And share it not an example here. Yeah, if you do balancing, you know that technique as a hash balancing. And if you do balancing of encrypted message, someone here knows what AEAD is? One. Okay, I'll explain. AEAD is when, along with the encrypted message, you can do an encrypted part at the beginning of it. But if someone changes that part, the encrypted part will say there is an error of decryption. So an encrypted part is able to be read, but at the same time, it's protected by the SSL or whatever. Why do you need that for? For high-performance balancers. They cannot afford themselves to decrypt the entire message, and sometimes they cannot, aside of those Russian DPIs called SORM, or, you know, yeah, that's like local Russian humor if SERPs are here. How many SERPs are here? It's forgivable for you to not have any context. Yeah. So about those high-performance DPIs, they sometimes read the unencrypted part of the message to get hash of it and to choose the machine they want to redirect load to really fast. And that's called hash balancing. And that is what, for example, Telegram does. At the beginning of their messages, there is also a clear text user ID. And that is one of their security breaches, actually, but that helps them immensely. So experiments, you already know that. Controllable jitter, you already know that. Tunes. Oh God, where to start? A lot of them. So XDP zero copy. There is a chance your AF-XDP will fall back to a copy, and you need to control that. You need to explicitly turn that feature on, and if your socket creation fails, then, well, that's your mistake. The second one is shared UMEM. The thing is, it's not only a shared memory between kernel and user, but that is also a shared memory between one user and another. I mean, between one socket, one packet, one client, and so on, and another. That allows you to keep things compacted. Why, I'll tell you a bit later on the huge pages technique slide. So to spoil, you definitely need to turn that feature on. So yeah, huge pages. And the thing is, Linux kernel usually uses small pages, but you can enable pages which are as much as 1 gigabyte of capacity. Why do you need to do so? To not pollute your page cache and to keep some pages in the memory. You do madvice call, which says keep this memory in the keep this page in the page cache forever. And it stays in the cache forever. Of course, you pack into that page all of the things you need really tightly. And that is why, along with the huge pages word, you need to learn one more term. You need high memory locality for both data and instructions. And that is why your performance can sometimes suffer when you have turned on one, like let's say 10 kilobytes library. Why your binary file grows 1% and performance degrades 20%? Because your files have started to overload instruction caches or instruction page caches. And here, 1% of tuning can give you 20% of performance. So the keyword here is memory locality. Try to keep that. But at the same time, do not keep it to the way of false sharing. So each thread should have its own cache lines. Well, you already know that, and I think it's already explained to you some of that you need to pack things tightly. And I won't focus on it that much. Let's go. Huge pages. Yeah, thank you. Busy poll. You already know that. Code. Yeah. So there is an example in C++, pk++. I'll give you a minute to read it while I am doing, guess what? You'll never guess. So, the code. That code has backend of AF-XDP, and that has some overhead, honestly. But I think that is good enough to use it in everyday code until you need to go somewhere deeper. And all the magic goes in the def-receive packets. I want to highlight the code here is not energy efficient. It starts constant busy polling, and you need to know that, folks. It's just the more deeper you go in the low latency mode, the less of CPU you have remaining. You are forced to constantly ask devices whether they have something for you. And a little spoiler, you are forced to constantly ask your application code the same. So signaling and coroutines are going out, and log-free queues, hello, log-free queues. Well, about real-world applications, I thought I would mention a few things here, but found only Cateran. So Facebook decided to do a balancer on top of the AF-XDP, and I think that's a wise choice because that would be a trade-off between performance, between throughput and speed, and the cost of maintenance. And my heart here goes to the Facebook. Facebook, you go. Yeah. So to summarize, you already know there's no extra copy and there's no system calls, no Linux network stack if you don't want that network stack. But you're still able to debug AFXDP. If you want to, you can redirect some packets by patching AFXDP eBPF code at runtime. And those will be accessible again via TCP dump, Wireshark, and so on and so on. So AFXDP here rocks as well. Well, not so much, because XDP hook is still in the kernel and you still are forced to do some work in the kernel. Someone here knows what netif receive SKB is? I'm not surprised, I don't know as well. But the thing is, XDP hook goes before that thing, as far as I remember. Or not before or right after, never mind. I honestly don't know that as much. I know that as much as you. The thing is just goes before 95% of the entire Linux kernel network stack, but there are still those remaining 5%, and they are affecting latencies. So, yeah. Get ready for the DPDK. That is the most powerful mechanism I know that involves your machine without offloading on the network interface. The DPDK is about occupying the entire interface and not getting into kernel at all. DPDK is when you have a user mode polling driver and when you have a polling driver and bypassing is zero cost, and it constantly asks network interface, you already know, is there any packets incoming? And when there is a packet, it goes straight to the user buffer. And there are clearly no fallbacks because there are no kernel buffers, no kernel involvement at all. Kernel just says, you are on your own. And I really want you to have a look at the experiments. Just look at that peak of latency around 2 microseconds. So latency is from 2 to 4 microseconds. Just imagine that. So it's like 50 times less than EPOL was. And even less jitter here. About the tweaks, I do not want to do a deep dive here. Mostly because of the complexity and also because of our timings. Yeah, mostly because of our timings. So let me keep it quick. One CPU core is one NIC RSS queue, and you need to pin cores exactly like that. You cannot afford yourself any memory allocations on hot path. You cannot afford yourself any other allocations other than monotonic allocators with 2 pointers. And you need to plan your load in case one of the clients is much more heavy than another, much more CPU consuming. So you need to somehow split it between multiple cores if things go south. But I think you already know that. So an important technique here is prefetch. Prefetching almost always does nothing on our home machines with our home code. But sometimes that matters. Prefetching is the idea to do a request for the CPU to load some pages or some instructions in your caches a priori, no, not the right term. So before the request, before the actual work. So you do a prefetch request, then you do some unrelated work. At the same time, in the meanwhile, your memory gets loaded, and after all, you are getting your memory without any delays. So best practice here is, for example, someone here knows how msync works with the default parameter. Yeah, I mean, msync is a thing to dump your pages, your dirty pages on disk or in memory. But msync in its default mode does not do msync. That's the pitfall here. It only schedules a synchronization request. And the best practice is exactly that. Schedule a synchronization request, then do some useful unrelated work, then synchronize with that request to do things in time without waiting anyone. will not bother you with code, especially given we don't have much time. The magic becomes at the last row, which is RTE, ETH, RX burst, which means busy polling. We are asking if there are any packets. And well, the downside here is when you're using C-style DPDK code, you are pretty much alone with all those TCP machinery. And what would there would be another option? There is, which is C-star library. And someone here heard of C-star? I see much more hands here, but I understand people are tired, so I'll keep it quick. C-star is a user space TCP stack on top of DPDK, and that is why I think you'd better use C-star first without diving into raw DPDK. I have tried, but failed miserably. And my mentor, after all, said it's a road to hell, and I'm completely agreeing with him. So in practice, Cloudflare is a ultra high load balancer which uses it like just not to die under the pressure it suffers. And to summarize, latency is 2 to 4 microseconds. You can use C-star on top of it, full kernel bypass, no course here. And the downside is, as I have said before, there's no kernel, so no multiplication of your network card. So network card is completely unreachable by other applications. So you cannot experiment with that thing at home and at the same time Googling how to fix some error. Because if you have one network card, then it will be taken by DPDK, and you will not be able to access Grok or Stack Overflow or whatever. So please keep that in account. Smart NIC. I really want to make a stop here. The ultimate overkilling solution. The thing on the right side is Cisco Exablaze, which is an example of smart NIC. That is when you don't go to the physical machine to handle packet at all. That is quite vendor locked because each smart NIC, they don't have much standards between each other. But that's very powerful technique when you can get rid of the machine at all. You can offload everything on the network interface. So smart NIC, you know, GPUs are complete machines in itself. They have their own memory, their own CPUs, their own mechanism of signaling, and so on and so on. Smart NIC has that as well. It has its own specialized blocks for computations, has its own something like CPU, has its own memory, and so on, but let me take another sip. Yeah, I won't bother you with the experiments, mostly because I don't have 5,000 for a Cisco Exablaze or NVIDIA Bluefield, but the latencies are even less than 1 microsecond, and sometimes they are even less than that. They could be something like 500 of nanoseconds or something like that, so completely blowing up experience. And about tunes, I will not do a deep dive here, mostly because I don't know myself. But the thing is releasing features on your smart NIC is updating its firmware. And updating firmware means updating constant read-only memory, and that is dangerous. So the thing you need to realize is to be a smart NIC programmer, you need to have no fear. No code here. Real-world applications would be, well, Exablaze uses it, NVIDIA Bluefield uses it, arbitrage traders use Cisco Exablaze and Bluefield. They use it for the most stupid but really fast models, such as three-way arbitrage or something like that. They use it in collocations, all of that is blazingly fast, and so on and so on and so on. To summarize, here is order of latencies. You have something like 10-fold speeding up here, 2 times speeding up here, and blazingly fast smart NIC here. And those two in the middle, in my opinion, are a chef's kiss, just like mwah. And what to use, you decide. And here, that's not like in the eBPF case when actually it's eBPF which decides. You decide. And I really hope you'll get successful in your experiments, and I wish you all good luck here. And thank you. Time for questions.
Thank you, Artur. Unfortunately, we are running out of time, but we still would like to have few questions. But when you ask question, please remember that your question is the only thing between us and Rodina. So anybody would like to be in between us and Rodina?
We have another thing. It's excursion for a rubber hand.
It's alternative to Rodina.
No, it's not alternative.
It's
additional
it's
to
mandatory.
Rodina.
Is it mandatory?
Yes.
So it just makes things worse.
Excursion is mandatory. Rodina isn't.
Folks, it's questions time.
So Rodina is calling, but we have call for questions.
Yes, please.
Oh, and try to be quick. So with DPDK, you still have kernel running for other stuff. Can you remove kernel entirely and just use bare metal code? Will it be faster?
Well, I don't think it would be faster because, well, you occupy one CPU, kernel occupies the other. So not sure if that would be, but thank you for a nice question. Something else?
What's your favorite SmartNIC?
I don't have such, but people who worked with it, it was another team. They've had something Exablaze based.
More questions? Well, if we don't have more questions, you still can ask Artur when you reach Rodina.
Yeah.
Rodina has nothing against questions. Just question him.
Or slide into my DMs. Email and Telegram are on the slide. Thank you, folks. I think it's time to go.
Yeah, no. It's not time to go. It's time for you to go.
For me to go.
Maybe 5 minutes ago. Yeah.
Thank you, Artur. Indeed, we have 2 more questions between excursion and between Rodina and. Please.
We lost QR code.
Okay. This one. Please rate this great talk. Please make your smartphones and rate. And this is first of the things. Да, давайте я по-русски тоже скажу. Пожалуйста, оцените доклад Артура. Следующая вещь, которая находится между нами и баром Родина, это вот этот QR-код, по которому вы можете оценить нашу конференцию в целом. Мы хотим поблагодарить всех наших выступающих спикеров за сегодняшние доклады, потому что это было очень круто. Женя, поблагодари спикеров, пожалуйста.
A huge thank to all our speakers. Miloš, Alex, Dusan, Kostya, Ivica, and Artur. Thank you so much for sharing your expertise and telling us about really interesting and practical stuff.